Welcome to APEC. It is August 29th, 2026. I'm your moderator, Tim Ventura. Thank you to everybody for joining us on today's call, along with everybody watching us on YouTube. So we have a lot of stuff going on. Dr. Charles Buhler will be discussing the Exodus Propellantless Propulsion physics. And then after that, Andrew Aurigema will be discussing Exodus as well. And the difference there is Charlie is our theory and physics person, and Drew is the world's leading experimentalist. So I am really pleased and pumped up to have both of them discussing the latest work they've been doing. Their organization and their research has been growing rapidly. They have made headlines around the world, so it is absolutely amazing. Another thing that I am really excited about is Mark Sokol has a demonstration he'll be doing after that. He has some new material he'll be presenting, and he'll be giving us updates on his work as well. And again, Mark, he is co-founder of the APEC conference, but he is also an experimental powerhouse. He has built and tested just design after design after design and gone through this list of experiments that have been out there for years. So I am absolutely pleased as punch. So I guess my thought also would be, remember to follow us on YouTube. That is the Alt Propulsion channel on YouTube. We streamcast across several different streaming platforms, but that is probably our primary. Visit us online, altpropulsion.com. I would strongly recommend that because I have been doing website updates for quite a while now, and I will be doing more. I'm adding in materials that have been featured not only on APEC, but also in our community. And I am doing organization and reorganization of those materials for everybody. The goal for us is to create a resource that the community can use to learn, grow, share, and hopefully shorten that path to this breakthrough propulsion goal that we all share together. So before anything else, let me bring Dr. Charles Buhler on the stage. Charlie, welcome, sir.
Tim, thank you for having me. Thank you so much.
Oh, it is truly an honor. It is it's a pleasure to have you back. It is an absolute honor to have you. So I'm putting your slideshow up right there. Exodus and the third order. I will not say that image looks familiar, but I may have seen that on TV. So
Yeah, well, it's the first order, but as close as I could find to it.
Yeah. Well, if it's okay, I will just take myself out and I'll let you roll with it. So there is a back and forth button on the slide share. If you put your mouse over it, you should see a little pop up there. Okay. And I will be here in the background. Just let me know if you need any help, sir.
All right. Thank you, Tim. Appreciate it. All right. Well, welcome. Welcome to Exodus in the third order, where I will be continuing my talk on the QED version of our Exodus thrust force. We've been very busy, but I will try to recap what we did at APEC a few years ago, and then talk about where we're at today. So, as you recall, these are not very new slides, but as you recall, we've had many discoveries of this force, this test force we've been looking at, Drew and I, for the last 10 years or so, and it has some very peculiar components. It's got an x squared dependence on the thrust as a function of the voltage or field. It has a linear dependence, and it also has this curious constant term to it. So we've seen this, obviously a few hundred times over a variety of different thrusters. So just keep that in mind. That's what we're trying to figure out, where the heck that's coming from, and what we've done in the recent years to explain it. So these are some of the thrusters that are online. People have started building them, which is very exciting. They've been following us diligently since the Danny Jones podcast, and our website is up, and now I am full-time Exodus to help Drew in the lab. So here we go. So, oh no, this didn't show up properly. But so I don't know if you guys can see it on my screen, but I can sort of see it. A bench. I don't know if you can see that, but what you can see here.
Charlie,
Yeah?
sorry to bother. If you want to send that over, you uploaded that as a PowerPoint, probably, right?
Yeah.
Yeah, PDF works better. It has to interpret that, and it's trying to interpret the. Yeah, if you want to send it over in the back end, I could put it up as a PDF.
Can you convert
Or if you want to just do save as and upload it that way. And I should apologize.
it? I didn't have time to do this. Give it to you, Tim. Do you want to go ahead and send it to you?
Yeah, go for it. Yeah, I will. Or if you just do save as PDF, that might be even faster.
Let me try that. Let me try. Apologize.
Oh no, it's
Technical difficulties. Let's see here.
yeah, no stress, no stress. I know it's
you guys are very patient with me, which is why I come. Let's see if I can do a
well.
save.
The nice thing about StreamYard is it leverages all of the built-in browser features in Google Chrome, but some of those are a little bit different than we're used to. So okay, and then it'll ask you to upload. If you just upload a new version, I'll switch it out for you.
Okay, just 1 second. Let me put it back where it's going. It's going to do it here in a minute. It's going to print the pages. Right. So I'm going to go to
Yeah, and ordinarily I wouldn't cause trouble for you, but I can tell you put a ton of work into this, and the last thing I'd want to do is have it like not represented well. So,
well, what's interesting though, it didn't save it as a PDF, which I'm very surprised as. It didn't do it. Okay, that's weird. Maybe I can just send it to you, Tim. Maybe you can figure out.
Yeah. I'd say send it over, send it away, sir. And
sorry. That's weird. I don't know. All right, Tim, I sent it to you, buddy.
Awesome. Okay, and I am just waiting for it to come through.
This is what I get for waiting to the last minute to finish this presentation. I've been so busy. But so do you want to turn this off?
There we go. Okay. Yeah, so give me 2 seconds. Okay, and give me just a sec. I will be right back. Here.
Ooh. I hope Charles has designated an experiment demonstrating the new force he described on Jesse Michael show. Yes. The answer to that question is yes. And I think my colleague Drew will talk about some of the experimental results that other folks have done, which is pretty exciting. We're going to put them on our website. It really messed the slides up pretty bad. Tim, I think you're muted. I can't hear you.
I was going to say it's Monday all week long. I will have it uploaded for you in about 2 seconds, sir.
All right. Appreciate it.
So because I am uploading it, it is going to ask me to thumb through slides. And so let me,
That's fine.
yeah, so just let me know when I need to go back and forward, and then we will, if you want to start over, that is totally cool. We only lost a couple of minutes.
Yeah, we could just start on the next slide. It's fine.
Okay, so it is working.
Okay.
And well, why don't we, if it's okay, why don't we do, if it's okay, let's start over from scratch. Would that be okay? And
Sure. How do I there you go.
okay, that's our slideshow. Yep, perfect. Okay, so let me put that back. I'm not sure who put that up, but I don't want that up.
Okay.
Okay, so yeah, take it away, sir. And yeah, if you start from the top, and we're good to go.
All right. No, welcome to Exodus. I'm going to discuss the third order perturbation theory that explains our forces that we've been seeing for the last 10 years, and going to continue on. So this would be probably the second of possibly a three-part, hopefully not, QED presentation. So it's a continuation from last August, a year ago, that I presented. So Tim, you can go to the next slide and we'll just recap what we're trying to do. All right, so here we go. So this is some of the early 2018 thrusts, the T-blade thruster, the ones that have been put online. People have been reproducing them. They haven't shown us results like this yet, but we expect them to come. We've seen them. They've gotten the thrust. They've gotten the right magnitudes and everything. They haven't plotted anything, but we are excited to see third-party people, delivering thrusters and making thrusters of their own. So as long as they're being safe with it, not hurting themselves, we're all for it. So you can go to the next slide, Tim. I covered that one pretty well. So to really explain the thrust, what I initially did, this classical theory, is I postulated that the force is proportional to the electrostatic pressure times area, and that popped out of conservation of energy, and at least in the classical sense. That was nice, but it didn't explain the experiments fully or get close enough to the experimental explanation until I force fed an alpha in there for one of the fields. So I had to do a transformation from the free charge to the bound charge by paying a quantum price of alpha in the free charges. That kind of matched up with experiments a lot better. That was kind of ad hoc, and it just basically told me that we need to do a quantum version of this. But even if it was ad hoc, it was at least useful. So we kept going with it. There's a couple of interesting things about it, which is really, really perplexing, that you have a constant term there in EB squared, which is the bound charge field squared, which is easy to measure from the experiments. It's easy to measure that when the power's off. And in this case, you multiply by 2 alpha, EB times epsilon naught A, and you get the second term. So just knowing what you get from the constant, you can go back and say what the middle term is. What is the linear magnitude of the thrust? And they match up in the experiments, which is quite strange, but at least we know we're sort of on the right track. So let's go to the next slide. Obviously, the classical theory wasn't completely correct. There were a lot of experiments where the ax squared plus bx plus c, where the a term was negative. Obviously, the classical does not predict that. The magnitudes are incredibly high, or very small in some of the alphas terms. The first terms and second terms are very small magnitudes. And obviously, the bound charge is a much higher term. But we did do this for many years. So we have a lot of these graphs for a lot of different types of thrusters. So that's basically where we started. So nothing new here. So let's go to the next slide. Okay, so what does a quantum theory of the force need to show? Well, first it has to be on the order of alpha squared. So it means it's a lower energy than the Coulomb energy. The force needs to be a function of the applied voltage or field, as well as the voltage squared. That's what we've seen experimentally. There needs to be a coupling of the pressure to the charges in the system. This is something that the classical does not show. There needs to be some kind of coupling, some kind of product between the pressure that you apply and the charges that it acts on. The classical theory doesn't do a very good job of that. So it's too remedial. It needs to be a little bit more complicated. The general form of any quantum theory has to match the experimental results across a large variety of thruster configurations, and there are dozens. There are many types. And obviously the biggest one, there needs to be a quantum mechanical explanation of why the thrust stays on after the applied voltage is turned off. That is a big head scratcher, the non-zero constant that we see in the experiments. And the most interesting thing about that constant is it is a classical term. So we have a quantum mechanical effect that reduces to a classical form. So my goodness, so the requirements, the constraints put upon physicists to try to find a theory that does all of this is incredibly difficult. So I had to start where the physicists would always start from in terms of forces, which would be perturbation theory. So I did this last year. I did third order perturbation theory. We went through the math. I know everyone here did it too because you're all excited about QED and you wanted to do 20 pages of math. So you all did it. And if you did, you'd get the next page results. You could switch it, Tim, to the next one. So you get this awful term. You get 12 terms instead of the usual 4 terms that you do in the Coulomb law to try to explain these forces. There were a lot of good things about it, but there was a couple of bad things. I do have a disclaimer here. We have this integral over d3k to the k to the 7 halves. I did find a third order example in my notebooks that didn't multiply them like this. So I don't think that 7 halves is correct, but that's okay. I can still move forward with the theory. And so what I've done is I've kind of simplified it a bit and just looked at the amplitude. So this talk is basically mostly hyper-focused on the amplitudes. The discussion of the momentum I had at length in the last APEC talk. I don't like to give the same talk twice. You guys can go back and look at it, but all of the terms here are relevant, but the ones that are most exciting are the ones with the coupling between the Q and the Q squared terms. So looking at that single term, that's the one we're kind of most interested in. That's the one where I believe the forces come from that are quite unique. And according to just simple dimensional analysis, this integral of d3k to the 7 halves, whatever it comes out to be, we could talk about that later, but it has to have units of 1 over length just to keep this in terms of energy. So we'll talk about that also. So here's the general form. It's a little bit complicated, so we're going to rewrite it. So go ahead and go to the next slide. Try to clean it up a little bit. So testing the theory. So the first thing we do is we kind of get rid of that k to the 7 halves for now. Just put a generic function of distance, and that's basically the distance, the Coulomb distance, or not the Coulomb in this case. This is a different energy, but the separation distance, f of r. So we do know that it has to be 1 over r, at least, to have units of energy. So the first thing we wanted to do is write it in terms of the fine structure constant, alpha, to see where we're at with alpha. So we did that here in equation number 1. That is this new third order energy in terms of alpha. So then I went ahead and looked at it and say, I think I can simplify this a little bit more. I realized that this HC, h bar c over 4 pi epsilon naught to the 1/2 has units of field times area. And it actually matches up to Gauss's law for a single particle, which is basically elementary charge E over epsilon naught. So I have a very short time, or a very short constant now in front of my in front of my Q1 and Q2. So this is a very simplified form of the equations. So this is probably a starting point for most of the what follows work. So we have this new theory. I'm very excited about it. I finally decided to test it out about a month ago. It's like getting a new car, so you want to take it for a spin and see how it works. So we have to do the checks and balances first. Make sure the engine works, make sure the cars works, make sure it runs. So we're going to go through that, and then we're going to go see what this sucker can do. So go to the next slide here, Tim. So the first thing we have to do is we have to make sure it's proportional to alpha squared. Any third order perturbation theory has to be proportional to alpha squared. And one easy way to do that is just to replace the charge with the unit charge times the number of charges. And if you do that, you'll get a transformation of E cubed. You could do a little bit of math, knowing that E squared over epsilon naught equals 4 pi alpha h bar c, and that reduces to that. So you do see that at the base, you can write this energy in terms of alpha squared. So that's at least consistent. The next slide, we have to show that it's at least an order of alpha weaker than the second order, which is Coulomb's law. So I'm starting with Coulomb's law on the top there, H2, which we're familiar with, the Coulomb energy, E squared of 4 pi epsilon on R. And no one writes it in terms of alpha, but you easily can. So I write that in terms of alpha. And then I write the third order perturbation theory in terms of alpha squared, just from the slide before that. I just take the ratio of these two and you get alpha. So that's good. So we're self-consistent between the second order and the third order. So that all works out. So that's nice. That's what we have to do. So we've done it. Now let's go to the next one. Next slide. All right. So now we're going to look at the general form of the solution. So the general form of this solution, I have to take all the terms that have the Q1 squared and the Q2 and Q1 and Q2 squared, add those up. And then what I do from this point on is I actually just write things in terms of fields instead of charge. Fields are easy. Fields you build. Areas easy. Areas you can build to make it a more useful form. So I did that here. And you get the energy is proportional to linearly proportional to an electric field. In this case, I'm just using E2 as an example, and quadratic in E2 also. So you get not only the linear form, but also the quadratic form of your answer times this F of R. So that's the general form. So we could stop there and be done, but let's go do some examples real quick. And I didn't have time to type all this up in the paper, but let's go to the next slide. We'll just take this sucker out for a spin and see what it looks like. Okay, so we can start with this. So we have a single set capacitor. I'm not going to go through all of these things, but you can write these by hand. We are in undergraduate world now, so we are done with all the QED. We're just doing pretty simple undergraduate E&M stuff, and we're just going to do some self checks and balances. Okay, we have two places. One field goes this way, one field goes that way. Is the field zero? Yes. You can go to the next slide, and Tim, you can go to the next slide. Okay, so now you can shrink the plate down, you make the plate in half. You can keep the field the same. You certainly can do that. If you do that, that would be your force. And the answer is that. And that checks out too. You can go to the next slide. I'm not going to read through all of these, but here's another one. You could do this again. You can keep the Q's the same this time instead of the E's, and you can go back and forth things. And you can show that the force here is zero. And that also works out. So that's another checks and balances. So you got a lot of things you can play with this in this equation. You can keep going. Tim, let's go to the next one. So this is the T-blade one. This is a bit different field, different area, much different little beast. Force goes to the left as expected. That checks off. So I didn't fill all these with numbers, but you can go to the next one. You can keep going. Dielectrics is another thing you can add in here. The force changes the function of the permittivity. We know that, shown that before. That matches with the experiments, and we can measure the permittivity with our thrusters. We've done that also. So that's not written here, but you can also take the derivatives. Don't forget the energy is just the energy, but the force is the derivative of these fields. So the fields can diverge. They don't have to be constants. So you also get the not only the electrostatic pressure force, but you get the divergence force also here. All we have to do is take the derivatives, and of course, force is the derivative of our energy. So go to the next one. And then you're going to have different U's, different areas, different E's, non-zero if this one's equal that one. All the little self-checks that you can do. All right. What's the next one? And many, many more. So there's a lot more. I wasn't allowed to share them all. Make the lawyers angry, but trust me, there are many more examples of this. So you have a new form of not Coulomb's law, but another law, third order law, that you can play with. It's a nice toy. It does cool things. There's a lot of really interesting things. So let's go to the next slide. Oh, now for the fun part. This is where it gets fun. So let's hit it. Go to the next one. All right, bound charge for Q. So there's our general form up there. And now what I'm going to do is I'm going to insert Q, but I'm not going to insert just any Gauss's law value of Q. I'm going to insert one that I think best fits what we have always struggled with is the bound charges. How do you understand the physics of the bound charges? So what I've done is I've got Q in there, and I got 4 pi epsilon naught r squared E2. That's basically the bound charge of, that's basically the field of a bound charge, or just a single charge. And I throw that in there. So in this case, I put it in Q2. And so you go through some math, and the math is a little bit tedious, but it's nothing like QED. And then you can start to see how the constants change. So, so Tim, why don't you go to the next slide? This will all be recorded. They can sit there and do this on their own time. But essentially, what you get is you get the we can rewrite the Q's back in terms of N and E's like we've done before, but you can get the energy in terms of alpha again, which is what we like to do. And what's neat about this is it went down by a square root of alpha, just with that one substitution of the bound charge. And what's weird about this one, we haven't seen the forces being proportional to the square root of alpha. But if we put in our guess at our function of r, we could put that in here, take the derivative, we'll actually see that the force is not dependent on the separation of the charges, which is very odd. It's probably why we haven't seen this. That would be very surreal if that actually happened. So maybe that's not a real physical case, but since we've reduced alpha by square root of alpha just by putting in Q1, or in this case, yeah, Q1 in terms of a bound charge, what happens if we put the bound charge in the other Q? So you know where I'm going with this. If I get a square root of alpha with one substitution, what's going to happen when I put it into the Q squared term? So let's see that one. So Tim, you can go to the next slide. Okay, so now we're going to put the same point charge Q1 for the bound charge for Q1 squared instead of the Q2. And when we do that, very interesting things happen. You get 4 pi epsilon naught squared divided by 4 pi epsilon naught to the 1/2. And that reduces to 4 pi epsilon naught h bar c to the 1/2. You get all the algebra works out now. And there's more math to this, but I didn't include it all. Where the alpha actually goes away, cancels out, just by simply putting in the charge form of Gauss in here. So this, to me, is very exciting. So the bound, what I call the bound, it's not what we typically say. Bound charge in this case would be injected charge. The injected charge into a dielectric has an energy given by this term at the bottom here, epsilon naught over E, r to the 4th, E1 squared, Q2 times F of R again. And it doesn't have an alpha dependence. So this term is probably considered classical in that respect. It does not have the fine structure constant in it. That's very cool. This was not expected at all. This was not at all expected. I only found this out a couple of weeks ago. And I was like, oh, I got to tell Tim about this one. This is really awesome because what this tells us is we started with a quantum mechanical form of the energy, put in the right form of charge in terms of a point charge, which is a simple thing to do, and it pops out that it doesn't, it just removes the alpha. That is pretty awesome. So now let's see what this gives us. To go to the next page. All right. Starting again with the generic form, we have what I call the free case, which is basically just put Q's Gauss's law for a generic form of E field and area, and then divide that by the bound case, which is the Gauss's law for a very specific form of point charges, and divide them out. So the energy for those two, the ratio of those two, the E fields fall out, the Q's fall out. You're basically left with alpha times area 1 squared over r to the 4th. Well, area over r squared is the solid angle. So alpha times the solid angle is the ratio of these two energies. So alpha has always been thought of as an energy ratio between the Coulomb's law and a photon of the same length between the two charges, but never been derived. Here, alpha has actually been, I don't know if I'd say derived, but it's been found to be the ratio of these two energies in the third order divided by a solid angle squared. This is really cool stuff. So this tells me how alpha is working in the problem, what it signifies. And I think I have graphics of that. So go to the next slide, what I think alpha is doing here. So alpha is basically on the right there. You're looking at um, an injected charge. It's got a radius to some surface and the solid angle omega on some area. Okay, Gauss's law can be used to find the field of any shape at all, any generic shape. You can flat plates, cylindrical plates, triangles, any shape you like, as long as the field lines are parallel to that surface. So let's go to the next slide. What I think might be happening is far away, you'll have those parallel lines from the field. But as you get closer to the bound charges, we have to make the transition to a 1 over r squared dependence of the field, because the field is no longer linear. That transition to the microscopic is alpha. It is basically the monitoring of the fine structure. So whoever named it correctly. But that's what alpha seems to be. So I think that's pretty cool. That's a cool definition for alpha. Um, it's pretty cool that this just popped out. I didn't ask for all that. I didn't want to see that. Didn't expect to see that. But if you go to the next slide, you can see what this does to their system. So going backwards now to the classical model, the constant there was epsilon naught e squared a. That was the original constant. The new one in the QED version of the third order is epsilon naught e1 squared q2 r squared, or 4 pi e. Well, what the quantum does, it's the same answer, but it defines area. It defines the area that you're dealing with. And that area is the number of charges in 2, the number of charges 2, which I can talk what that is, r squared over 4 pi. So basically your area divided by r squared, your omega, your solid angle, is the number of N2 particles divided by 4 pi, which is steradians. So, and that's really the difference. And it actually explains what the heck the where the bound charges are. It's really exciting because it shows you that there's an E field from the bound charges. It puts their image charge in Q2, and it acts on the area of where Q2 is. So let's go to the next slide, what I think it's doing. So you have these little bound charges and acts on the area, the solid angle area, not the Gaussian area for a flat plate, but the solid angle from the um, from the bound charges that make their way to the free charge area. I know that's a lot. There's a lot there, but essentially your Q2s to the right, essentially your E1 is the little red circles, and you keep adding those up N2 times, and you'll have your area from the classical example. So that's pretty darn cool. So you keep adding that up. That's your area for your bound charges. It tells you where the field is coming from, what it's acting on, and where it's going inside your system. It's a far more descriptive form of the bound charge that we did not have access to in the classical realm. Completely blew me away. I was very excited about this. This is one of the most exciting things I've ever seen, because it explains something I can see in the experiments but have no way of deriving. So I'm excited about this. So I went back and I said, okay, let's see if this is still self-consistent with the models. So if you go to the next slide, you can do the constant terms from the classical. You can rewrite them. You get the forces from the constant to match the second term in the fit very nicely. This is what we did classical. The question is, can you do this again in the quantum one? So I think the answer is yes. So if you go to the next slide, you can see, sorry, that didn't come out real nice, but you can take a look at this. So if you get the C constant from your experiments, and you can put that back in to get your B term, and it checks out that it actually does work. And you can use either one of these constants either from the classical or the quantum to get the right answer because they match up. So anyway, that's where I ended, but that was awesome. So I am very excited about it. So I hope you will take the time to look at this and digest it. But it blew me away that the QED version of this could actually have any impact at all on the classical term, the constant, and it did. It had a very profound impact on it. So I was very excited about it.
Charlie, that's amazing. That's absolutely amazing. We definitely, I'll bring all the guys. In fact, I'm going to bring everybody in now. This is, yeah, this is so big. Like my brain is kind of half fried from it. But okay. Well, guys, before anything else, let's put our hands together and give Dr. Charles Buhler an enormous applause. And Charlie, thank you for your patience as well. Thank you for your patience with the technical bugs and you know, the StreamYard glitches and all that stuff. That's part of APEC, right? It's like, but yeah, I am so excited. So when you were describing that, this is just my thought, and I would open this up for you guys to have questions too. We have plenty of time if you're open to it, Charlie. This sounds like an EM shielding explanation for gravity and inertia almost. Is that way off base or?
I wouldn't go there yet. Right. EM shielding is great for electromagnetic waves. I don't know how this fits with gravity, to be honest.
Yeah. There was again, I like years ago I read about Lesage, the shadow gravity idea, right?
Yeah.
And then different people have proposed, you know, maybe this is the strong force tapering off, and maybe there's like shielding of these other forces that happens, you know, by molecules, and that's why gravity exists. But when I saw the slide with the bound charges, I was like, that almost looks like another shadow force or like a shielding effect, kind of.
Well, I mean, I think obviously Lesage, I have a lot of respect for that theory. I think I know it's been discredited, but
Yeah.
really the only real theory of gravity out there. I mean, Newton has laws, Einstein has laws, but doesn't explain how it works. Why is mass bending space-time? Why is that happening? At least Lesage has some kind of mental model for what's happening. And if that's the case, you would be able to, at least look at this and say, well, if fields exist, then pressure exists. Pressure exists. Maybe Lesage is on the right track, just had the completely wrong model. It wasn't photons or anything like that. Maybe something else. But yeah, I don't know. That remains to be seen.
Yeah. Well, it's exciting though. I mean, and the reason I'm so happy to have Drew come after this is you guys have arrived at this through experimental work, and then you're like building the theory on top of that. And for me, that is so tremendous because you've got results to start with, right? It's like it's like, how does this model explain these results? And I think that's the way the best science is usually done.
Yeah, I think we're very fortunate to have, almost 2,000 results under our belt, which we have not published, and we haven't really shared it with the community very well. That's my fault, but it is definitely useful because we know what to expect in the experiments. We know what the answer should be if it's there. We needed a way to model them, and so we've had to develop this theory over the years to account for that. But I couldn't have been happier with the QED part. I think that just blew my mind. I didn't expect all of that. I expected the pressure to act on the charges. I expected that the Q squared, pressure acting on Q. That was an expectation. That's why I went there, because this is what we see experimentally. I needed an explanation for it. Everything else is absolute bonus. So it was pretty cool. Yeah, I like it. It's fun, and it's a heck of a lot of fun to do, for sure. But I'm going to let Drew talk all about the experiments and all the careful experiments that he does to get these results, because they're not simple. There are a lot of issues with the experimentation that you have to overcome.
Well, let me open it up and see if anybody else has any questions. Do you guys have any questions for Charlie?
I do, if I may.
McCulloch, go for it.
Okay, Charlie, I haven't seen any dependence on vacuum energy of your equations. Have I missed something?
It's the vacuum, basically, whatever. No, I'm not doing Casimir effect. So no, this is
No, I
just.
know, but
I'm
the
not.
energy has to come from somewhere.
That's true. Yeah, I mean, all of these perturbation theories do they do take in that energy from K-space, right? From the vacuum. That's how it works. That's where photons come from. That's where the scalar photons come from. That's where the virtual photons come from. So that's in the framework of QED. That's where the energy comes from. It is the
But you see,
vacuum.
the problem is this: if you look at QED, is 10 to the 120. Okay, that's not possible, really. It's too much. So that there has to be some kind of vacuum energy density, and I'm looking for someone who at least done something to point this out, because I don't know, because it has to come from somewhere, and we have to have that value.
Well, you're probably not going to get it from this any more than you'll get it from Coulomb's law. You're
I
not going
know, but
to.
you have to have it.
I agree, but maybe the stuff that we're doing, and maybe the stuff that Sonny White's doing with the energy, maybe there is some way to measure that vacuum level. I don't know how, but he and I both kind of feel the same way about this. We don't think it's infinite. Okay, we think that not that it can be used up, but that can be washed out, perhaps. We don't know, but we kind of get that feeling. It's not an infinite supply here. If that makes sense.
No,
Yeah.
We have no way of showing any of that. We have no way.
No,
of
that would make sense. That would make sense. It's like it would almost be like something on top of a base or level, and you can take it down to that base, and then it hits an absolute bottom, right?
Yeah.
Temporarily, and then
it's just a hunch, if you will, experimental hunch, but we have no way of testing that.
now we know that we at the bottom, okay, but it's not it's not zero. It has to be something, and I would like to know what it is. Okay, so
well, McCulloch, I think that's a valid question. I mean, sure. I think kind of what Charlie's suggesting, where my mind also goes, is like break that down into a more discrete problem to solve, right? And then and then the stuff that Charlie and Drew are doing, that's like one more. It's one more tool in the toolkit. Right. And then like what Sonny White's doing is another tool in the toolkit. And once we have enough of those tools, we'll have wrenches that fit for this problem. Because I think it's really intriguing. I mean, and like the Casimir effect.
It's kind of how I look at it too. Just it's another probe into it.
To be honest,
the universe we don't understand.
Well, I mean, Sonny absolutely blew my mind when he did when he did his announcement on the Casimir. I was like, wait a minute, 0-point energy? I did not think we'd see that in my lifetime. I'm like, how is this happening?
But the point that you're gonna get as a criticism, because where's the energy coming from? You have a thrust, okay? So your device or your spaceship is going to have higher and higher speed eventually, so higher and higher kinetic energy. Where the hell is that coming from? That's what people will pick.
And I completely agree with them, because I have no idea. But I have the same problem, right? I mean, you have the same problem. You have two charges, and you stick them on a piece of plastic. They'll stay there forever. Where are they getting the energy from? That force doesn't go away just because, I let go. I turn off the power supply. Those charges still exist, and there's still that Coulomb attraction forever.
Yeah, same for magnets.
Where do they get the energy from?
Could we say that this is like an open versus a closed system dilemma, right? We're saying, okay, this is part of a larger system. That energy is coming from a larger system. We're just not going to fight that battle today.
We're not going to fight that battle today. That's right. That's how I would read. And it does. It hurts the brain to think about. It does.
Does it really?
They don't have an answer.
Does it really matter where the inertia or momentum or whatever is coming from?
Oh, Drew, I think you have your headset on, but I think it's using your other mic. I think if you go into your mic set in StreamYard, it has a selector for input mic.
It does matter to answer Drew's question, because people would pick on, okay, you basically, where's the Lorentz invariance and stuff like that. Yes, that's
No
what people
doubt.
would pick on. Okay, no matter what your experiments say, most of people would pick on these things because that's how it is.
Yeah, Michelage, I think that's valid. Although at the same time, this is work that's ongoing in progress, and there will always, I mean, you've seen this as well as I have. There are always critics out there, and at some point, you just have to say, look, you're trapped in your paradigm. You know, the experimental evidence says something different. This is the road that we're taking, and you know, we're making progress, and it's one day at a time.
No, I agree,
So-
but just I
so
would.
I have
I'd
I
like
have
to
a
know where
question.
the energy is coming from. Okay, to just from my,
I have a question, guys. And good to meet you, Dr. Charles. So one of the things I noticed you're saying you did a third order perturbation there, and I'm just kind of wondering a couple things. One is, you know, I don't know if you're aware of there's actually a kind of a challenge or by Clay Mathematics Institute for the Young's Mills and mass gap. Basically, there's a problem with perturbation theory in that, like, you can't go to too high level of energy before it breaks down, right? Before you start to get things that don't make sense, that are unphysical, and that's why there's a search for a non-perturbative quantum field theory, right? Not that I agree that that's the right path, but that's, you know, it's a recognized problem. So that's one question, and I guess I'll stop there. I'll save the other question. Have you considered that maybe you're going too far with the perturbation theory in terms of energy, where it's no longer valid?
No, I mean, you know, it's a lower energy, right? So we're probing even lower than the second order, because every order is much lower by a factor of alpha. It's not getting higher; it's getting lower. But yeah, I don't know. There are a few third order examples out there. I was looking at one in my notebook, but like, why the sky is blue. It's a third order perturbation experiment.
Yeah.
So, you know, they still use third order perturbation theory for many other experiments and many other theories. But yeah, I don't know, Curtis. That's a good question. I mean, where are the limits of perturbation theory? I don't really know, but I do know that at least when I was in grad school, that was the way to do it. But that's changed, and awesome and good to have something else.
Well, I mean, it's an open challenge, right? There's a certain amount of money. It's a prize that you can go get if you figure out, you know, specifically. And of course, they tweak it so it has to be what they think it is, which the answer probably won't be that. So yeah. No one will get the prize. But anyway, or maybe they will. Who knows? Maybe they'll be open-minded. But the other thing I wanted to address is this whole thing about the vacuum. I know that Hal had done a paper, Hal Fern over at Cal State Fullerton, back before he retired. Basically, we have an bird, by the way, so you can hear that. Sorry about that. But,
that's yours. Okay.
Yeah. He's a young guy, so. But yeah, so there's a paper there where Hal actually studied and you know, because one of the things that people alluded to is that, okay, inertia is maybe an electromagnetic effect. That was kind of like a hypothesis out there, where there's like a plasma of electron positive background pairs, as Mendel Sachs like to call it, and then you could densify that and do things. So basically, there's a paper that Hal did, basically showing, and I'll share that with you guys in the link, so you can look it up. I think it might be relevant to what you're trying to do here.
Yeah, the stochastic electrodynamics, that the stuff. Yeah, gravity.
Charlie, if it's okay, I just wanted to bring up a question from the YouTube. Your definition of alpha is a ratio of 3 to bound charge electrostatic energy. How does that coefficient appear in your force measurements, and how does it scale with the area as expected?
So in the experiments, we measure the force as a function of voltage or field, and it's got a quadratic term, a linear term, and a constant term. And the linear term and the at least from what we can tell, has an alpha in it. So we see that experimentally, but we kind of put that in there to make the experiments match the data, because we needed to get 137 from somewhere. So we stuck that in the classical model. It wasn't until we did the QED model that kind of helped validate some of that. We knew we were dealing with a quantum effect. There's not too many lab experiments that you could do in your house that can probe alpha, but we think this is one of them. So it's just an experimental artifact. But it is a very important one, because it tells us, A, that we're in a quantum world, which is what we are, and then B, two, that we have a difference between two types of charges and how they behave. There's only two real charges that we have. We have free charges that you make with a power supply, and then we have bound charges that you get from static electricity, rubbing a balloon on your hair. Those charges might fundamentally be the same, but the way they interact are different because of the environment that they're in. And alpha, I think, is a probe of that. I did not expect that to be so well defined in the third order QED, but it seems to be pretty well defined that is the distinction. So I don't know. It was cool, pretty cool stuff.
Oh, and this is one other question. I think I could answer this too. Doesn't the energy just come from the battery? But you've seen that these devices don't actually require power, other than just overcoming the inefficiencies of your system, right?
Yeah, we definitely put energy in, but it's not being converted to kinetic energy through the classical way that we think it is. Because when you turn it off, in theory, this keeps moving. It doesn't stop moving. So at some point, you're going to overcome the energy that you put into the system, because you would have translated a huge distance, and that's way more than we can account for from our battery or voltage. So most of these things start with power, but the energy that they can use are much higher than what we put in there. So there's another, there is the question of the energy. Where's the energy coming from? It's still a valid question.
Right. Another question that I would ask is, do you see any upper limits to this? Like, can you reach 0.99C with such a system if it keeps pointing in one direction?
I don't really have a good answer other than testing that in space and see if it can get there. No one wants us to do that experiment, and I don't blame them, because that's a dangerous thing to do. But I don't have a good answer why that wouldn't happen. The rocket equation, the relativity, all of that.
There's no rocket equation equivalent to this.
I know there isn't. So we have relativity or special relativity. There's nothing to tell us that it's just going to stop moving at some speed.
Would this be? Do you think could you call this a Mach's principle thrust in a sense?
I don't know. That's a good question. I don't know.
I have another question.
Hold on,
Basically,
Tim, can you hear me?
Yeah,
Yeah, I can hear. Yeah, Drew, you just don't have the right mic selected. I think it's plugged in. You just have to.
Okay, so you're saying I still sound really far away?
Yeah, you still sound really far away.
It sounds better than before, I think.
I agree.
Yeah, but the headset is
I have another
definitely not
question
on.
for Charles.
Is that any better?
No, your headset is not on. I can
Drew?
tell you it's not on.
Do you want to sit here? I do have to leave.
Drew, you need to go in and select it. Go into your audio settings.
Yeah, I got the IT guy standing right here and tells me everything's right.
Welcome to use this computer. We're in the same building. You're welcome to use, because I have to leave. My wife is working the Roman Space Telescope mission.
So Charles, maybe one question for you.
I don't think he knows.
Here.
He's making all that noise, but-
And that's actually basically a question to both of you, I think.
What was that?
So so you have this question of where's the energy coming from, which is not completely solved, but you have now this third order perturbation theory where you at least can calculate basically inertia being carried away from the system in an interaction that I would describe as an interaction with the whole background of the whole system, right? So this is how I understand it. Correct me if I'm wrong here. So the question if this energy supply is infinite could be answered by a long-term test, right? And I know that you have done kind of long-term testing before, but do you plan to have a thruster running for, I don't know, like a year and show that the force, like do a measurement if the force depletes at all? Or yeah, are you planning on doing something like that?
I suppose we could, if we come up with the right type. It would have to work in air, and the challenge that you'll have with that is you have to prevent the charges from recombining. So no matter how insulating your system is, there will always be some leakage, even if it's femtoamps or less.
Yeah.
So,
But why focus on propulsion? You can focus on energy extraction, what Sonny's doing, you know? He did the same thing. He started with warp drive and then he moved to energy. So it may be a better application to use basically, you know, big windmills.
Yeah, that's so now we have two companies. Now we have two startups. Exodus Energy. I love it.
Yeah, well, yeah, pivoting. So I do have another question, experimental. So have you considered doing a null test where you have one surface that's supposed to be going one way and the other one the other way? It should actually cancel, right? If that effect is,
Yep.
You have this theory, you can actually design a null experiment. And actually, I have the null experiment, the last one that Jim made, which was the piezoelectric stack. Instead of having an aluminum mass or aluminum plate and the brass mass, it had both sides had, you know, a small brass mass that were equal. So that was like our null test that we were going to do. So we had that, and then we had the asymmetric one, and we could show that, okay, one gives us a force and the other doesn't, for example. So yeah, are you guys, now that you have this theory and you have an idea of what the theory is saying that the mechanism is, have you devised a null test? Are you going to devise a null test that can?
We have. We do that all the time, really, because we always like to test our Faraday cage. People don't like our ITO box, right? It's transparent and it's got holes in it. We always make the thruster with grounds on the outside, but to test a null thruster is very useful. If I put, 4,000 or 5,000 volts on a thruster, I want to make sure that it doesn't go to attract to the chamber, because of Coulomb attraction. So what we do is we'll do a null thruster, which is basically two plates at the same area, just like the same thing you were talking about. Put the same voltage on there and watch nothing happen.
That's kind of like what we did today, Charlie. The test that we just ran today. Basically, we ran it up to full voltage, and it did a tiny bit of nothing.
But it wasn't, that was experimenting with the design. But we do have null thrusters they're just the same area plates or same size, shape, no asymmetry, no thrust, no attraction to wall. So we do that, but only as in the context of trying to shore up our test methods. Because a null thruster is a very good test of our system and how well we're Faraday shielding, because we get that a lot. Are you feeling properly? Because if you're not, you're going to get attracted to different things. So null thruster is a way to do it. Crank up that voltage, just put it on a non-thruster.
Well, and guys, we're at the top of the hour. So, and we're going to go to Drew, and Drew and I may have some mic check stuff to do, but that's totally cool. So
can you hear me now, Tim?
You sound
Drew,
perfect.
You sound amazing.
Okay, I had to drag the computer over here because this.
You sound amazing. It's perfect. It is perfect.
Awesome.
Yeah.
Awesome. Just for you, Timmy.
Thank you, sir.
I do have to leave. I'm sorry. My wife is.
No, that's wonderful, Charlie. Thank you so much.
Bye,
Before you go, guys, let's do this. Let's put our hands together and give Dr. Charles Buhler one more applause. Charlie, thank you so much.
Thanks for having me, guys. Appreciate it. So how do I get out of this thing?
Okay. Yeah, and actually, what I will do is take everybody out except for Drew. Okay, so Drew, thank you, sir. Okay, the dynamic duo, both halves of the powerhouse team today.
Yeah, loving it.
Yeah, no, and thank you so much for presenting on the experimental work as well. You and I did a podcast a couple of weeks ago, and man, your sound quality is just like through the roof today. I'm so excited. So
yeah, well, we're still working on our IT. It's a long, painful experience.
Yeah, I know. Do you want to do a screen share?
Yeah. So I just do a screen share, and because what I have is a PowerPoint presentation, and then at the very end, I want to run a video. It's
is it PDF or PowerPoint?
this is a PDF.
Okay, yeah. So for PDF, just click that plus button down at the browser.
Yes. Yes.
Yeah, and then
indeed.
slides and PDFs, and then
slides and PDFs.
And then scroll all the way down there to your computer.
Your computer.
Yeah, and then it will upload it. It'll ask you to upload.
Oh, we have to upload the file.
Yeah, for PDFs.
Okay. Okay. Let's see.
Yeah, and then the wheel will spin while it processes for a second, and this is all Google. This is all Google magic. It's all built. Most of it's built into Google Chrome, and then StreamYard does some stuff on the back end. I don't know.
PDF. Okay.
Yeah, and it'll take a sec to upload. There we go. Wait, yep, perfect. Okay, let me add that in. Yeah, and so then when you want to do a screen share, just let me know and I'll switch over to that. But this is the best way to do PDFs.
Sure.
So if you move your mouse over it, if you put your mouse over the screen, it has back and forward buttons, and they're only visible to you. And so I'll take myself out, but I'm saying take it away and let me know. Let me know if you need help or anything.
Thanks, Ram. Hello, Drew in sunny Florida. For those of you who don't know me, I put a little lead-in slide to my life. I'm a 40-plus year veteran of the U.S. space program, mostly ground support equipment, but a little bit of flight. And as you can see from the pictures, I build stuff. And my dream someday is I want to walk on the moon of Titan. And I have built hydraulics, pneumatics. I've built racing experimental aircraft, including designing the airfoils. I've worked on the shuttle program, the space station program, a couple of the CST-100s. In my hangar home, I have worked on Bell 47 helicopters, my personal rebuild, which is a Cessna. I've done experimental optics. I've built up to meter class telescope mirrors. And that's me in the far corner there sitting at my 0.8 meter research telescope that I built from scratch. So I'll just move on. When I grow up, this is sort of a joke, but it's a real joke. If spending endless hours of your precious free time fixing stuff that ain't broke, making stuff that don't exist, or generally wanting to be left alone so you can get some work done on your warp drive project that you've been tinkering with for 25 years, you may be an engineer. Note, if you are reading this on an APEC, you may be an alternate propulsion engineer. Truer words may have never been written. Okay, before you can go to the stars, there's sort of an engineering checklist, and I wanted to just kind of walk through it, because as much as you want to build a spaceship, you have to have a plan of some sort. So it has been my observation over the years that the first thing any sane person that's in an engineering field is going to talk about is, what is it that you're trying to achieve? This is like me talking to somebody and asking them questions, or maybe telling them how to move forward in the plan. So if you can't articulate what it is you're trying to achieve, there's little to no hope of actually achieving it. You don't have to have blueprints or specifications. You have to have an articulation of the dream, of the challenge. And it could be tiny. It could be, I want to know how to make a transparent plastic that doesn't melt at 500 degrees Fahrenheit or something, but you have to be able to articulate your dream. Then is there anything out there that looks like your idea? And with today, you can obviously search everywhere, almost immediately, and you might find drawings, or you might find it commercially available on Amazon or something like that. You just have to go look, see if there's anybody who's even remotely close. And if you can do a little bit of research, then you might find that there are groups of people like APEC that are into the same basic ideas of stuff that you're into, or that you can find maybe something from 50 years ago or 100 years ago or 5 years ago. But you need to do your research. Then it really, really, really helps to draw up a sketch, a plan, a goal, put something on paper so that you can go back and read it the next day and say, what was I thinking? And I put a little sketch there. That's the original artist concept sketches for the 1966 Star Trek Galileo shuttlecraft. Now, the final thing that showed up on Star Trek didn't look anything like that, but these were supposedly the original sketches. Anything will do. Stick art, paper, anything. Charcoal, it doesn't matter. You can. I think in a movie, the guy sculpted mashed potatoes into what he saw in his head. Make a paper and tape and string and anything else you can lay your paws on, mock-up. If you can't articulate it in true 3D, you're probably not going to be able to go much further. You've got to be able to at least bring it into the real world, out of your head and into something. Paper cups, tape, newspaper, it doesn't matter. You just build a mock-up. Make a concept of your article out of anything you have, literally anything. Tin cans or steel cans, styrofoam, maybe some blinky lights or something, whatever it is that can move you from just a paper and tape mock-up to any kind of a concept build. From there, maybe make as many prototypes as it takes for your idea to come into being at a level that you can actually test. Because if you can't test your idea, it's just a piece of art. And there's nothing wrong with art. I love art. But if you want to bring something into existence, then you really need to be able to run some tests on it. And that's kind of the premise of this whole conversation that I was going to have. You need to be able to test your idea to failure. And everybody says, oh, no, I don't want to test failure because if it fails, then I won't have it. Well, if running a test and causing your thing to fail happens and it kills your whole dream, you don't really have a dream that you can move forward with, because you are going to fail. You are going to build lots and lots and lots and lots of these things, whatever it is, and you're going to break them or change them or whatever it is that you're going to do. You need to make more prototypes. Don't be afraid to just build them. You can use the old ones if there's enough left of it, if you haven't burned it up or whatever, or go get some more styrofoam or whatever it takes to build a prototype. Not everything on a prototype has to work. If just one thing, if the blinky light works, then you know that your batteries aren't dead or something. So iterate, build on your results. Let's say whatever it is, you have a little widget and there's 20 things that can go wrong and 19 of them do, but one of them doesn't. Let's say the little blinky lights work. Well, now we know the little blinky lights work, so maybe the wires that lead to the blinky lights work, and maybe the batteries work, and maybe the switch that turns it on and off works. This is good. This is a good place to start. From that, figure out what the other 19 things that went wrong are. Expect failure. It's wonderful if you have success, but you don't expect it. Expect failure. Try to learn from it. You're going to have a lot more failure than you're going to have success. So you may even want to go the crazy route of celebrating your failures, because you're just going to have so few successes that you're never going to get to celebrate. So then the biggest thing, this was not mine, but I live by it, is learn to fail faster. You're going to fail, and you're going to fail sometimes a little, sometimes spectacularly, and sometimes it's going to look, sometimes your whole thing just up in flames. Those times are rare, and always have a fire extinguisher around. But you're going to fail. Learn to fail faster. If you can fail super fast, then you can iterate super fast, and hopefully you'll get closer to the thing that you're trying to dream. Test more, fail more, build more. That's my strongest suggestion, is never give up and never listen to the critics. Okay. Big headliners. These are monster things that you should know before you're headed down a path of a serious investigation. And the biggest one is costs do not scale up linearly. I found this out the hard way with vacuum Small vacuum chambers are expensive. They are ridiculously expensive. Large vacuum chambers are the price of really nice houses. So you find what it can take to get your job done. If it's a little electrical test bench and you need a nice fluke meter in order to check the circuit or something, well, they sell $10 meters that almost do what flukes do. You know, flukes start at $1,000, let's say. So you can go and do, like when I'm looking around the shop here, because I see so many examples of things we've destroyed over the years. We have an entire bucket full of the little $8 or free, some of them were free, of digital voltmeters. Maybe they may have even been swing needle. They're so old, but we burned them up because we were screwing around with stuff we didn't know anything about. We burned them up. Finally, we had a whole box of them. We were just going to give them away as souvenirs. But whatever it takes to get your test run, start out with the minimum. And if it turns out that you don't have enough resolution or enough capability, or you're just tired of looking at a transparent plastic vacuum chamber that can only get down to around 10 to the minus 2 torr, then scale up to whatever you can afford. And if you're blessed with a better half, make sure she's in for the ride, because a lot of times you're going to have to spend far more money than you may have allocated in your toy fund, and then it's always good to have someone else's buy-in. But just the core of this is cost do not scale up linearly. And I don't know what order they scale up at, but it ain't nowhere near twice as big as twice as expensive. So scale up in equipment, capability, and complexity as time and funds permit. And time and funds also covers really good friends who are there to help and teach you stuff. Like there's a shout out to my buddy Marty, who's a world-class welder. He taught me, he spent 30 years trying to teach me how to weld. He finally gave up and just did it himself. Start out small, work your way up to big. My first vacuum chamber for real was a little 12-inch chamber. It was expensive. Now I have a 28-inch chamber. It is stupidly expensive. But, 15 or 20 years separated these experiments. So you scale up in what you can afford and in what you have the ability to get, because you're going to need test equipment. If it's a for real goal, you're going to try and build something complex. You're going to have to test it in complex methods and with complex equipment. So, you can only test with what you physically have access to, whether it's, borrowed or loaned, or you buy it and play with it yourself. So moving on. Oh, this is a good one. Homegrown does not mean substandard. Everybody says, oh, I built it on my test bench. This must just be someday I'll be able to afford something that can really do the job. Well, that's true. Usually commercially manufactured equipment or power supplies or pressure chambers or gauges or something like that, they're usually very good because they've been beaten by people who've sent back the broken ones. And pretty much if you buy commercial, it generally does what the specs say it's going to do. But that doesn't mean you can't build your own power supplies. That doesn't mean you can't build your own high pressure chamber or your own vacuum chamber. As long as you're using quality materials and someone else's plan that's actually worked, you can build stuff that may cost 50 times the cost of building it yourself if you went out and bought it. We built dozens of high voltage power supplies and promptly fried most of them. Over on the, buy what you can afford and build what you cannot. A lot of our stuff rapidly left the world of you can buy it. Okay, you just can't go out and buy a small warp drive thruster. It's certainly not the container to put it in. This was back in the days when we were filling the inside of the tube with an inerting gas. I can't remember what we were using, but we found out real fast that argon's a bad choice and nitrogen's a bad choice, and a lot of other gases were bad choices. And we found out the hard way that if you put enough electrostatic field out, that the carbon fiber in the carbon fiber tubes that we're using as structural members, that transmits energy down the carbon fiber and shorts out your power supply. So, when you build, you're taking on all the responsibility of understanding everything about how this thing could work great or fail. So expect the unexpected. But again, you can build some really, really nice equipment, homegrown. That's always an option if you don't have infinite funds. Don't be afraid to build/test your vision. And you don't even have to understand the vision if you have people on your team. Some, as I have Dr. Charles on my team, along with, half a dozen others. Sometimes a vision that someone else has needs to be tested. For example, the giant curious blob of foam that's in the little tank. Well, the little tank is nothing but a bunch of balsa wood and some metal-coated plastic. It's ITO-coated PET plastic. And we built the whole thing, and it swayed back and forth. It was hooked up to a force meter, and it worked wonderfully. It's amazing that little homegrown thing tested out so well. And you can see other versions of other things that we built, like the whole high vacuum rig. They're up there, and on the far right side there is you can always tell the test engineer because he's identified by his or her professional attire, and the physicist wears whatever he has on. But it doesn't, simple doesn't mean wrong. So whatever your vision is, build it, and then build whatever test equipment you can think of to push the edge of the envelope and move forward. That's always the goal, is just build and move forwards. Control what test environment parameters you can. This is kind of a broad one. If you're operating in air, well, you've got to be able to breathe. So you might want to try and control the humidity. You might want to try and control the temperature. Now, humidity is pretty simple. You have to put an enclosure, and you have to put some kind of a humidity absorption system in there. Usually the little silica gel beads. You bake them out in the oven, and you stick them in there, and they suck the humidity down. And then find out if you're actually achieving anything by putting a humidity indicator outside. So in this case, it's 45% relative humidity just on the other side of the wall, and the the 38% was just inside the cabinet. So in this particular case, because we're working electrostatics in open air, which is a terrible combination of things to try and do, we decided to try and pull the humidity in the box down as low as possible. And it sort of worked. I mean, 38% relative humidity is better than 45. But we also were controlling the temperature. We were trying to keep the shop at the same temperature so that we didn't have all kinds of temperature swings to involve, because we didn't really know if the scale was temperature independent. Turns out that the scale has a temperature compensation built into it. Things like, if you can use a regulated power supply, then you don't have to worry about the voltage jumping up and down for your test. If you can use, if your thing is light sensitive, maybe have a controlled light source. If it's pressure sensitive, maybe make sure that you're not testing one time in the middle of a hurricane, the next time in a dry sunny day. Whatever the parameters are that you think might be affecting your test, you want to try and control them, and that might require more sophisticated test equipment in order to lock in on your base test. Because if you run two tests with the same exact thing and you get two wildly different results, either your thing doesn't like to be used twice, or your test conditions, something in your test conditions may have shifted. So if you can lock down as many of the parameters, of the environmental parameters as possible, you can eliminate some of the many questions that you're going to have at the end of the test. Because, you know, if you got 2 parameters, you got 4 possibilities of something being wrong. If you got 3 parameters that you don't know, now there's 9 possibilities of stuff that could be, you know, interacting or whatever. And it goes up fast. It gets to be a nightmare real quick. So, okay. This one's huge. I did not know this. I was taught this by our brilliant programmer, who told me that you have to live by these words. Never change more than 1 parameter at a time, because you're sunk if you know, this is just a cutesy little thing. Some guy's crunching something down, but if you say, well, I know I got 4 things that I got to change, so let me swap in AC, let me put a higher atmospheric pressure in, let me rotate this little crank faster, and let me move the time of operation from morning to night or something. Well, now you got 16 possibilities of what could have changed minimum, and you got all kinds of interactions with all the other parameters. You're never going to figure out what, you know, if it goes great, yeah, you're done. If it doesn't go great, which is most likely, then you have no idea which of those intercombinations, which of those changes, you know, what, just don't do it. Just save yourself the misery. Only change 1 thing. If you're building a mechanical system, only change maybe the diameter of one of the rods. That's it. Go back and test. Go back and test a whole bunch. Or if you're changing the frequency of something that's moving or something that's being energized, just change the frequency and see what happens. Don't change the frequency, change the pulse width, change the modulation, or switch to DC when you were running AC or something. You know, really, these are words to live by. 1 thing at a time. Okay. And then because this is APEC, I thought I would talk a little bit about an APEC-related test example. In this particular case, I can't show any of our newest thrusters because, like Dr. Charles was saying, the lawyers get all pissy about that. But atmosphere is a big thing. We don't generally test in open air because electrostatics and air don't mix well, and I'll get into why that's the case. But for the most part, these are 2 very, very different test setups. The same thruster would be placed on both of them. You would place a thruster on the top of that column. You would place a thruster buried way, way back inside there. And here's an example of the test rig that's buried down inside that thing. You'd put a thruster on that test rig way down inside that vacuum chamber. So these don't look anything alike, and they don't, for very good reason. There was some really smart guy, some physicist dude named Feynman back in the 50s, I think, and Charlie thinks he's like a hero to him. He said that you really don't know if something's real unless you can prove it 5 ways. So, you can put something on a scale, or you can see it move, or you got to have 5 ways to prove anything. So that's sort of been our driving function, is having different ways to test our prototypes and concepts and just ideas that are based on different parameters. An open air tester has the benefit of being able to breathe in the same general environment as your test article. And breathing is a really important thing. So we spent a lot of time and effort to try and get a setup that we could put a thruster on. And you may ask, well, why is there a big black plastic tube sitting in the middle of your scale? And the answer is these are electrostatic scales, or actually they're capacitance scales. And they're really screwed up by the leaking fields of an electrostatic thruster, which is really sad. So if you get the thruster anywhere near, I'd say within about 9 or 10 inches of the scale, then there's a very strong probability that the thruster will affect the scale in ways that have nothing to do with did it make thrust or not. So one of the things that we had to overcome was the fact that the scales themselves don't like this process. So anytime you see one of our tests, we're 4 inches, 6 inches, 12 inches, this is 16, above the scale. Then we put our thruster up there, we run the wires to it, and we run the test. And then we run the test and run the test and run the test, and then we flip the thing over and run the test some more so that we can see, are we thrusting up? And then we flip it over, are we thrusting down? And we flip it over again, are we thrusting up? Because it's real easy to get lied to. And air, although it's wonderful to breathe, and I'm totally pro air, I think it's an awesome thing, it is a horrible material in which to run ultra high electrostatic fields. The prime example is lightning. Everybody's seen lightning, probably. If you haven't, this is Florida, go outside and wait 20 minutes and you'll see some. 10 to the 6 volts per meter causes air to break down. So when you have a field, electrostatic field, and that's about 3,000 volts DC-ish, if you have a field, it will break down the air and it'll have a little burst of lightning. Well, that's bad. That's bad in every way for trying to create thrust from whatever. So you really have to be careful about things like the air, which means you have to limit the voltage that you're operating at so that you stay underneath the conditions that cause the environment and cause the atmosphere to break down around you. That's pretty much the problems for an open air thruster, is that you got to operate it at a lower voltage. You got to get it away from the scale. But if you, that and half a dozen other problems, if you pay attention to all of those and you work them out so that you get consistent testing results with a null tester and all that stuff, then you can use a scale, a very high resolution scale, to see the thrust that's created by one of our thrusters. That's great, because that's one way to show how a thruster works. You test it in open air. Well, that's not the only way. So let's say we want to test it in vacuum, because a lot of people say it's ion wind and it's whatever. So we're like, okay, we'll throw the thing in a vacuum chamber and we'll do the same thing. Well, that's a whole nother set of problems and a whole nother set of parameters. Commercial electronics do not like running in a vacuum. Sometimes the LCD screens just explode. Generally speaking, if your commercial electronics get hot for any reason, they can't dissipate heat in a vacuum. So they melt or burn up or do both of those things. And that's all sadness. In a vacuum, you off gas. Commercial electronics and commercial products and most things that are built on a 3D printer just give off gases when you expose them to vacuum. Well, that's the plasticizer leaving the plastic, so your plastic becomes brittle and for no reason can just break. So you have environmental impacts on your test equipment. You have environmental impacts on your electronics. Vacuum is hard to generate. Good vacuum, like really deep vacuum, like 10 to the minus 6, is stupid difficult to generate. But if you want to discount all of the naysayers that say it's ion wind, then you pump down to 10 to the minus 6 torr, and you run your testing and you build your electronics and you harden it for vacuum, and you run lots and lots and lots of tests. Other bad things that are about vacuum is once you close that door, you can't change nothing. I mean, you can change digital stuff. You can because this has a pass through. that lets USB information get in and out and power and stuff. But you can't go in there and physically reset anything. And it takes, you close the door and pump this thing down. It takes 12 to 16 hours not to pump down. I can be down to pressure in an hour or two. But that means that all of the surfaces that were just out here in the open air, which have molecular water on them, they still have molecular water on them. That water is just frozen. It just goes right from being technically liquid at that point, stuck on the surface, to being frozen ice on the surface at room temperature. Then over the next 12 hours, the magic of sublimation happens, and that water, those layers and layers and layers, 1,000 of them sometimes, of water go off and go wherever they're going to go into the vacuum, get sucked down and pulled out of the room. So it takes 12 plus hours just to dry out a test article. Well, over there in open air, you just know you have water vapor on there, and if you get up above, say, 10 to the 6 volts per meter field, it's just going to arc across the water because water becomes like a metal at a certain point. So you have to understand the limits of your materials and the limits of the environment. Vacuum, you have to dry things out. And it doesn't matter if you hit it with a heat gun originally, you can get it all nice and warm and you say, well, just stick it in there, because the molecular water comes back in seconds. And it takes 12 hours to dry it out. So if you do something and you forget to do something like hook up a wire or whatever, you don't figure that out until you're ready to run the test. And then you get to shut everything down, vent the chamber, open it all back up. And in that split second, when the air rushes back in, it screws everything up again because it puts molecular water on everything. So you get to pump it all back, fix whatever you messed up, change whatever you forgot to do, pump it all back down, and wait 12 more hours for it to dry out again. This is all part of the testing regime. So you really need to understand the effects of your test atmosphere is going to have on your results. Things that are tested in open air could have all kinds of miserable charge on it, which is generating false thrust, positive or negative, or maybe nothing at all. Things that are tested in vacuum, am I physically changing the shape of my test equipment because, I printed it in 3D on a 3D printer, put it in there, and all of a sudden it's outgassing and the plasticizer is evaporating. Things are changing shape that have nothing to do with the test. So sometimes you have to just take into consideration the environment that you're going to test in. And my suggestion is test in multiple environments, because, you got to be able to show it 5 ways. And those 5 ways can be close to each other, but they actually have to be different. You just can't be 5 different versions of the same test. They really, if you follow that Feynman guy's rules of the universe. Okay, hopefully there's still some people awake, because I know how boring all this is. You want to test the same configuration as many times as it takes to verify results. And I just threw up something. This is a typical test. Now, this test ran for about a week. Every one of those little orange cones is a video that could be anywhere from 1,000 seconds to 200,000 seconds. Every one of those little things is a screenshot, and there's no end of mischief. I just wanted to throw this up there because this was all the same test article, and it got tested over and over and over and over and over. And usually tests that are this exhaustive is when something works, because that really worries me. When things break, that's easy. You pull them out of the chamber and you tear them apart. And I do a forensic on after every test, and I look for things that are burnt or charred or blistered or popped or whatever. That's the thing. That's easy. When something fails, it's easy to find. But when something works, that's far more worrisome, because now you have to ask yourself, why did that work? So you test all of the edges of the envelope. It's like the old test pilots when they would jump in an airplane, they would go a little faster the first, they would go up and they would never retract the gear. And then they'd go up and they would maybe fly a little faster and a little higher angle of attack or something. They would test what they called the edge of the operational envelope. And they would go to all the edges of the envelope for testing before they ever do something like raise the gear, because that's a whole nother test. Then they'd go test the envelope again and make sure that they could, drop the gear. Well, when you're doing your testing, you want to draw on a piece of paper, the possible envelope of operations, X number of voltages, X number of frequencies, X current, all the things that you think are the edges of your test operations, and then run them and find out, hey, I thought this thing could only take 500 volts, or, I thought it would be at least good to 500 volts. And all of a sudden you find out the thing burns out at 300 volts. And then, this is sadness. But you might be pleasantly surprised and find that this stupid thing goes up to 15,000 volts. Whatever it is, test the edges of your envelope as often and as exhaustively as it can possibly be. And that's my suggestion is whatever it takes, do it over and over and over again and record everything. Computer hardware storage is cheap today. Okay, I think I'm getting really close to the end. So this is just an example of record everything. Display as much information as you possibly can on the results, because it's really nice to have a presentation at the end of your test that shows all the information that you had and what did what. So things like a date, a time, some kind of description of your hardware, because you run 500 tests, it gets a little fuzzy going back a year or two, because you might go 6 months with everything working great, and all of a sudden you realize, oh man, something was really screwed up, and you got to go back 6 months. If you don't have information as to what you were doing, and by that I mean serious records. Okay, this is an engineering notebook that I record and put test examples in, and all kinds of stuff. Data, graphs, whatever. You don't need to record what you had for lunch that day, but pretty much everything else. And this is a real typical example. This is about a month or two from this year. So that's, I got about 100 of those things. So record everything. Even if nobody else ever looks at it, eventually you're going to want to go back and look at your own stuff and say, what was I thinking? Put it on a screen, because again, making data make sense is not that difficult. You can use webcams, you can use screenshots, screen saves. This stuff is cheap and easy to do. So it's really, really, really worth the hassle to put your data in some form that makes sense. Like, for example, this particular one, I'm kind of looking at the middle of the screen towards the bottom. 1 hour of runtime at 6 kV generated negative 25 milligrams of upward force, which equates out to 250 micronewtons. Okay, well, that's great. Well, I happen to have kept this test running where 16 hours at pretty much the same voltage, pretty much had the same thrust. And then at 16 hours of runtime, then 1 hour at 0. So in other words, I turned it off and wanted to check to see what it had done. So I've been running it for 16 hours, and then I turned it off, and I measured the results. It turns out it was still making around 220 micronewtons. And I saw some questions in the comments. People are saying, well, when you turn it off, why does it still run? It still runs because we're injecting charge into the dielectric, which does not like to have charge injected into it. So if you inject charge into the dielectric and you remove the free electron field, the dielectric, the charge that's in the dielectric is still in there. And it's going to take days to weeks for it to come out of there. If it's in there, it's creating field, because charge is what creates field. Voltage does not create field, charge does. So however the charge gets stuck in your toy, until it's gone, this stupid thing's going to continue to do whatever it was doing. And that's our particular case. So in this case, I ran it for 16 hours and then I took it off, turned it off, and an hour later it was still making charge. Now it had bled down some, obviously. 220 is not 240 or 250. But if I didn't have some words that told me what I did, I'll go back and look at this thing 6 months later. I invented this whole thing and I wouldn't know what I'm looking at. So do yourself a favor, put as much information on a piece of paper as possible so that when you go back and look at this, or God forbid, try to explain it to somebody, there's something there to help you, because nobody can remember everything. At least I can't, and I have tried. Let's see, we're getting real close to the end. I do not like computers. In fact, I loathe computers. They are right up there with electronics for how much of things I hate. But a graph is worth 10,000 spreadsheet entries. I record 250 cycles, or 250, I record 250 cycles a second, and my test can run 300,000 seconds. This particular test, I really can't tell. I think that's 50,000, 60,000 seconds, something like that. In this test, there would be 250 data points, and I record probably 40 pieces of information times 240 or 250 times whatever this test was, 60,000 seconds. That's a lot of data. Nobody can process that kind of data. So put it in something that makes sense. You know, whatever your test is, if it shows force, or if it shows frequency, or maybe little blinky lights, I don't know what it's going to be. It's going to be something awesome, and it's your data, and you want to present it in a form that's digestible, so that maybe you can see trends, maybe you can see directions of coolness that are happening. So just, figure out whatever it takes, which in my case is go find your genius programmer friend, because I don't know how to do any of this. And he builds these amazing Python routines, and boom, it just spits out all the data. I mean, this is the backup force meter that tells me basically what's going on with the chamber in general. This is the thrust that the system saw. Voltage. Let me see what the voltage was. Yeah, we were down here at about 5 kV. This is some other problems. This is the temperature. So obviously the temperature kind of slid down a little bit, came up. This is the pressure, hovering somewhere around 4 times 10 to the negative 6. This was the temperature of the meter. That's not as good, same as outside. Anyhow, without labels and data and something visual, your billion data points are worthless. So get to whatever it takes to put this out in a format that this test and the next test and the next test and the next test are all in the same basic idea, so that you can start to see trends from one test to the next. That's just a really good accounting problem. Any questions? I think I had one slide after that. Oh yeah, ept.space. Shameless plug for our website. And Dr. Charles, this is his favorite saying, it ain't rocket science. So I'll go back to the questions. No, I'm going to leave it on that one because that was cool.
And Drew,
how can I help?
Yes, I will bring myself back in, and actually, let me see. I will actually show the real website. It may be. I may show.
Yeah, it's even better.
There we go.
I have a 5-minute video that I can start up whenever you tell me how to do it. Yep, that's us.
Yeah. No,
and
absolutely.
Our new IT guy, you saw him a little bit, probably an hour ago. He's making this beauteous, and it's awesome.
Looks gorgeous, man.
And our media section is almost up to date. Almost. So we invite anyone to come. You can actually send information to that. I think it's info@ept.space, and I actually do read them. I've got about 600 of them ahead of yours if you send one, but I promise you I will read them, and unless they're obnoxious, or don't bother just telling me I'm an idiot. I have enough
Okay.
information on
It-
that.
And so that is there. It's not, let me see. It looks like it's not showing the video that was playing in the background, but there's a cool splash video. So for,
Oh yeah, there is. Like the moon.
there it
there's
is.
Mars.
There it is. Okay. Yeah, what, for some reason it didn't display on mine for a sec. So let me see. What I would do is go in and do share screen.
Okay, go in and do share.
Yeah.
Is that this button?
Yep. And that should stop that there. And yep. Okay. So do share screen. And then you can just share it like oops, Drew disappeared.
I think I threw myself.
Okay. Sorry about that. Okay. So click the share screen button at
That's
the
the
bottom
thing.
of the screen.
That's the little screen with the plus in the middle, right?
Yes, sir. Yes, sir. The little screen with the
Okay.
plus.
Oh, okay. Yeah. Okay. And then share
Yeah,
screen.
Yep. And then it will give you the
Oh, okay.
options.
Share screening is easiest with two monitors. Yeah. Do not show these tips. Screens. I guess just share screen. Okay.
Yeah.
Oh,
And then it will pop up and I can
working on
swap it out. I can swap it out. Yeah.
Entire
And Drew,
screen.
I'm really excited, man. I'm really excited. So one thing I will do is I will do breakouts of these.
Yeah.
So I will take yours and I will take Charlie's. I will render separate videos of these and put these up on the Alt Propulsion channel too. So you
Okay.
guys will get the attention that you need. And I will do Mark's as well, because I think Mark has a big presentation for us. Okay.
Well, I
so,
see something, but I don't. Do you have to do something, or do I just click on this thing I see down here?
oh yes, that's my fault. Let me stop sharing and now I will share it there.
Okay.
Okay. Perfect.
Here's the deal. Out of the blue, like I said, we got about 600 emails after the podcast. Please go watch the podcast. It's really cool. Charles is much better than I am, but it's still pretty cool. And it's available on the website. You can go to it. Completely out of the blue, we had a guy who built a thruster and sent us this video, and this is amazing. This is better than the video that I made on how to build the thruster, and he got better results. He actually started out at 20 micronewtons of upward thrust on his little, you'll see, and then he sent me another thing that said he actually got it up to 100 micronewtons of thrust, and this is like 6,000 volts. So I'm very impressed with this, and I'm just going to show it and stop talking. There is no audio to it. Sorry. How do I? Oh, I guess I just do this. Okay. And this is what he built it with. Can you hear some jingle noises in the background? Because I can, but I don't know that it's going to show up here. So anyhow, he wanted to prove that his power supply worked. So he built a little electrostatic cylinder rotator, and he figured out there was something wrong in his high voltage power supply, and he fixed it. And then he got his little electrostatic thing to spin. And then he discovered that if you take a digital camera a little bit close to a field like that, it screws up the camera. And we had a little chat about that because I've been emailing him back and forth. This is his build. And he opted for thinner pieces of styrofoam, but with the added insulatory properties of a Kapton tape, which is perfectly acceptable. This is his design. He based it on our basic concept from the patent, and then he jazzed it up so it fit his capabilities and his materials. And he gives you a full description of what it is and how it is that he built it. He obviously thought that soldering was within his capabilities, so his system is soldered together. Mine, I think, was all taped together because I don't like solder. It tends to melt the styrofoam. So here's all of his materials, and you can see the basic layout. It's a T-blade, and then he, I assume, goops it all together and builds a little structure. He does this safety thing, and remember there's lead in the old solders. That's an old Radio Shack solder, so there's lead in old solder. So you want to be real cautious about leaded solder. Lead poisoning, vapor-driven lead poisoning is no joke. It's real. So here's his awesome setup, where he shows that it's a kind of little high voltage. Oh, I'm sorry, that's probably a 20 kV power supply. He used a different one later, and then he does some zeroing, and then he turns it on. Oh no, he tested. This is perfect testing, by the way. Test your test equipment. Excellent example of a simple but very elegant test. And then he throws a switch, and it goes. I can't remember if this is up or down. I don't know which one it is. Yeah, it goes down. So it's essentially pulling upwards. It's very difficult to make a scale go upwards. Very, very difficult. Scales can go down for lots of reasons. We haven't thought of any of them that can cause a scale to go upwards. So he's doing tests that's somewhere in the 50 milligram range. That's about 50 micronewtons. 20 milligrams is 200 micronewtons. So, and then he went ahead and took his thruster and put it on a piece of styrofoam and put a different power supply underneath it, and different batteries and stuff, and hung it from a thread, and it turned on, and he recorded his data and ran his, continued to run his testing. And then he ran it a bunch of times, obviously. You can see that. And then he put it aside for a day or two, and the electrostatic properties that he didn't know about screwed it all up. So he thought he broke it. So he took it all apart and put it all back together and ran it again and got even better results, because he cleaned up his work a little bit. So you don't be afraid to break your toys. And if something happens that you don't understand, by all means, reach out to somebody who might be able to explain it to you. You might be able to figure it out on your own, or you might reach out to somebody that's been down the road before. So either way, this guy made a 5-tier thruster that just absolutely rocked. Just absolutely rocked. And this is out on YouTube. He said anybody can look at it. We're going to put it on our website. So we're stoked. This is we've had a couple of these of videos over the years, but this is probably the best one. And just to show that the electrostatic system was doing what electrostatic systems do. So yeah. Total kudos to the guy who put this out there. Really, just absolute. He rocks. So I'm going to go ahead and stop presenting. I think I stopped presenting. I don't really know. So that's it. That's all I got. Questions?
Drew, you are a rock star. Rock star. Okay, let me bring everybody in and we will clap to demonstrate your rock starness. Drew, thank you. And you went through awesome experimental. You have been like reiterating those experimental points for like several years now. And so it was awesome that you went through all of those, especially like only change one thing at a time, right? Like, so it is good to see a bundle of those. And again, I am going to slice and dice in my video editor and get up another copy of these on the Alt Propulsion channel. And I'm just pleased as punch to be able to have both yourself and Charlie present. This is actually we have like less formal presentations, but this is kind of a super big day. If it's okay, I want to very quickly share, folks. This will be like a 2-second share. Well, actually, you know what? Let's do Q&A first. I'll come back after that. So guys, what do you have for Drew on his experiments?
I gotta tell you that listening to you, I was basically looking in the mirror. This is so point engineering stuff that it's unbelievable. I have to congratulate you on that presentation.
Right, thank you. Engineering is not, it's just repetition. It's do it and do it and do it and just never stop testing. Never. And usually it's boring. And you didn't see any technical drafts. You didn't see any documentation that I showed where it had, a full grown, like blueprints, like, 10,000 pages of blueprints or hundreds of pages of test experimentation. I've done all that in my career. Well, when I'm home and doing homegrown stuff, it's just go do it and record what you have to and then move on, because you can get lost in documentation. You can spend all of your time and money and energy on documenting. And don't get me wrong, documenting is good, but you don't need a formal presentation for every single test, 100 pages of test preparation, and you just don't need it.
Well, the thing that strikes me about what you do is this. I'm taking this back a few years. Mark does the exact same thing, and Jared does too. But like, I have seen, the way that I would put this is some people think with their hands. That's the only way I can describe it. My first wife's father was a career machinist, and like, you could just hand him a tool and he would intuitively know what to do with it, what its limits are, and then how far you could push it and how you could use it for different things that wasn't really intended for, right? And it's like, it's just a different way of thinking that is like hands-on and engineering focused. And that's a lot of the stuff that you're describing. When I visit you or I visit Mark or when I visit Jared, I see that. I see that you guys are doing hands-on stuff, and like, especially like with Mark is doing this wide variety of experiments, and like, he is reusing tools and equipment for different things, that they weren't always intended for. So
I have a question for Drew. You don't have to answer this if it's proprietary, but what are the limitations of this technology and how do you plan to overcome them?
Our current limitations are scale. We're small, and the test articles I can put, that chamber looks big until you stuff it full of test equipment. So right now we're in the 6x6 inch general size, 0 to or 1 to 20 stack. So we haven't really found an upper limit, but there's a realistic limit. The materials we work with weigh something. The stacking process weighs something. So I'd say if everything breaks in our direction, which it never has, then maybe we can get to 1.5 Earth unity as a
Looks like we lost Drew.
his connection just stalled.
1.5
Am I
Earth
back?
unity. You're back.
Wait,
now.
he's back. You're
Maybe
back.
not.
No, you're here.
Okay.
It's just, yeah.
So, I don't see Mark. He disappeared.
I'm here.
I think we're having StreamYard issues. That was kind of hitting me with Charlie too. There was like a delay and some stopping. But, oop. That or Florida's coming in for another hurricane. We'll see.
Looks like we lost Drew as soon as he said 1.5 Earth unity.
Yeah. Well, what we could do, we'll give him a sec to come back. What we could do also is, Mark, you have a big demo. You have lab stuff and a big demo, right?
Yeah, we have a live demo, and I have Mini Mark over here as an assistant.
You have an assistant with you.
Yeah, and also Henry is over in the back over there.
Wait, there's Drew is back. Drew is back. Okay,
Sorry.
I'll bring him in. Oh, and I just removed him.
Yeah,
Sorry.
So I don't remember what I was even talking about.
Well, 1.5 Earth
Oh.
unity.
Thank you. I think we've hit 1.8 Earth unity, but it was a super rarefied example. It was a single thruster all by a little lonesome. These things love to work by themselves. They don't love to work in stacks as quite as much. But I want to get to where I think this technology can get up to 1.5 Earth unity, which, there's not a size associated with that. That means if you have 10 tons of propulsion, 10 tons of propulsion materials, then you have an extra 5 tons of spaceship mass. So the first 10 tons is going to go with to lift its own mass. Okay, because you got 10 tons of propulsion material, so the first 10 tons of thrust is going to go just to lifting its own mass. And God help you if it flips over, because then you're really screwed. But I think 1.5x is probably the edge of the envelope with this particular technology. And it would take some getting to get a stack, to be able to get 10 tons of this stuff up to 1.5x. That's my guess. I don't think Charlie even thinks it's going to get that high. He thinks this is really just the get us in the door, the little toy thrusters, which it may be. Right now we're at 0.5 Earth unity, and that's our advertised thrust ratio, which is more than enough to build small thrusters and even big thrusters. But
any plans to take it to space?
Yes, there are. We hope to be in space within a year. In fact, we were just talking with a space-rated power. They make power supplies, and they're huge. They're in San Antonio or something, Texas. They just happen to be here for the launch. So Charles knows everyone in there. So we're going to talk with them. We're going to see if we can afford a space-rated power supply from them to go in with our plans to be in space within a year or less, possibly less than a year. So we're totally excited. It's 7 days a week, 24 hours a day to get there. But that's the dream, is to get up there, and if it works, you'll know about it because their plans are revolutionary.
It's amazing.
Our customers' plans.
So, guys, we're past the top of the hour. If it's okay, would it be okay to close things down for Drew? I will do a super quick walkthrough because I did tell everybody about the Ivo drive, which I know Drew hates, but I did a podcast.
I don't hate
on
the
that.
drive. I just don't like the physics.
But let's do this. Let's put our hands together one more time for Mr. Andrew Aurigema. And Drew, I'm sure you'll probably stay with us and chat all day, but I did want to say, I cannot thank yourself and Charlie enough. It is so wonderful having you guys back. It's also, to see your guys' company grow the way that it is amazing. And then after this, we're going to go to Mark, and I feel exactly the same way about Mark. He's got amazing company growth, amazing results. Everything is going the right direction. It's super, super cool. So let me very quickly, one of the things that I put on the email was, because I was intending to play this, but I'm not going to torture everybody on making them sit through it. So I will just share. Okay. So on the Alt Propulsion website, and I will be adding Drew's and Charlie's as discrete articles too. Very quickly, this is the Ivo Drive article. I'm going to do a breakout of this. So just the slideshow that I did will be up there with him. But I did a podcast with Mike McCulloch on the Ivo Drive and Quantized Inertia, and we ran through kind of the experimental results from their orbital test, which were inconclusive, but still exciting. And then I also did one on UAP warp drives with Chad Wanless. I did one with Charles Chase from the Unlab, and he talked about the Casimir effect and his matter wave laser. He also talked about quantum vacuum propulsion. And then I did one with Chance Glenn on experimental space-time distortion. And so those are all new and they are all up there. A lot of folks have already seen these because they're following me on Twitter and stuff. So this is the same thing. What I'm going to do is break out just the slide shares there. And I have a couple more coming in the next few weeks also. And I do want to try and do an actual podcast interview with Dr. Charles Buhler. And if I am able to do that, the cool thing about that I would be able to take the material from his presentation and use that to create focus questions and slides. I'm trying to do slides a lot more, although what I'm finding is the AI tool gets confused and cranky sometimes. So every now and then it just turns around and beats me up for no reason. So that's kind of my super quick update. But I would say the thing that I'm really excited about is not only are we seeing more results and getting more material out there, the material that's out there, we're able to organize it more effectively, right? It's like slowly but surely, and it's definitely slowly. Things are getting more organized. Because like you guys, I mean, I'm sure all of you guys have done this. Like I used to take books down to the photocopier with a bag of quarters and, and so there are lots of folks out there who still have boxes full of papers, and people have emailed me and said they print out pages from the website because they want to lose them. And I'm like, oh, okay, that's cool. But like all of us have this rat's nest of information on our hard drives or physically that we can't deal with. So Mark, do you want to run through some stuff, man? We'll go to lab time.
Yeah, I wanted to ask you which one you want to do first. We have an inertial propulsion experiment that we're going to run live, and also the Alzafon. I know you have some slideshow that you wanted to show for that, and
you know what? I am not able to get the slideshow ready fast enough. I started on that. It did one slide and it did it incorrectly, and I'm like, okay, I cannot pull this off with like an hour left. So.
Okay. Yeah, Henry, just the bottom of that. You can take that. We're about to get a second camera on this. So this is one of the projects that we spent the entire summer working on. It just was kind of like a side project. So you guys probably remember this from back in the day, the gyroscope swinging arm thingy. Mike Gamble was working at Boeing. He built a similar device. We built a much larger one. This kind of just swings back and forth. It does produce a little bit of propulsion, but it has a drawback. First of all, the thrust to weight ratio is horrible. And secondly, the propulsion only works when it's in a gravitational field. So we put this on ping pong balls, and it would slide around. It would move, based on your inputs. You'd have to swing it in one way faster and then return slower, and that would sort of like inch its way forward. The thing is, if this was in free space, what would happen is it would swing up and down. And that up and down swinging is not what we want. We want it to actually move freely. So I came up with a new design called the triad gyroscope, where instead of having two, we put 3 gyroscopes together. And building it was quite a challenge. Let me show you guys what it is. Now, there's 3 gyroscopes together. The reason why I'm running this for the first time live is because given the amount of forces in this device, there's a high likelihood that this thing's going to fail in some way or another, even after giving us positive results, whatever happens. It's on a swing arm over here. So there's a lead acid battery on the other side, and we can move the lead acid battery in order to balance everything out. And then it's hanging from a swivel on the ceiling. So basically what we have is 3 gyroscopes. They are all controlled from this center point with a piston. An air piston pushes this threaded rod. It's like threaded on each side or basically it's like a gear, similar to the way those wine pushers work. And these arms can swing back and forth based on that. And we have the input of air is being provided by our air compressor. Now, no air is coming out of this. So the air that goes into one side of the piston comes down the second line and vice versa. The air output is from the knob over there. So we shouldn't see any thrust coming from that. And then separately, there are 3 motor controllers, each controlling one of the gyroscopes, just the onboard motor that turns the wheel. Now that was also kind of tricky to get that to run. And that's all controlled via remote control. This is Henry Goldstein. Henry Goldstein is about to graduate high school. He came down. He's been very helpful with a lot of these projects. Sometimes you find people without the PhD that are better than the PhD, and that's Henry. Henry. Yeah, he's actually local, and he comes by and freely gives his time to us to run these cool experiments. So I believe that because there's 3 gyroscopes and they are set 120 degrees from each other, that the translation of force would move it forward or possibly twist it. 2 possibilities. Somebody suggested that we could also add another axis of rotation. I'm not even sure how we could possibly do that, given the limitations, but we're going to give this a shot. I set up the Insta360 camera over here. We'll set that up so if anything does happen, you will see it happen. Again, with live experiments, lots of things can go wrong. So bear with us as we power it up. Okay, Henry, you want to hook up the power? We have a power supply over here. We're going to power that up. We'll start winding up the motors. They're on 3 separate controllers. I'm going to move the laptop back a little bit. This thing, oh, we got a fire here. Yeah,
Not the fire?
Nope. Yeah, but that was a problem. I think the voltage was too high.
Oh, it
See if it
smells
works.
smoke.
Yeah,
White smoke doesn't mean it'll stop working.
Yeah, this one overheated. I think is it possible that it was a wire draw? No, we tested these.
Yeah, this isn't. Is there any shorts?
They all work, right?
They
It
were.
looks like it's from A.
Yeah, it was coming out of A.
Yeah, it's off.
Off?
Yeah, I saw it.
From B now.
Burn right there too.
Okay, we're gonna have to swap that out.
Yeah.
Okay, well,
Just turn it so
I could we could still run the other part of it. That's the nature of live testing.
Oh,
We're gonna run the air compressor part and see what happens. That will swing it back and forth. Okay, here. Put it, attaching it. 3, 2, 1. Okay. Okay, it needs a little higher pressure. Try to release it. It's stuck. It needs to move forward. There, yeah, swing it forward.
I don't know.
You ready? There we go.
There's.
No, it's not moving back. Okay, we're having lots of trouble with this.
oh my goodness.
Let's leave it right there. See if we can swing it back. There we go. Yeah, it tends to stick a lot. Let's see if I can get to do the swinging motion at least. I think the voltage was too high on the power supply. That's why it burnt up.
Yeah.
Oh,
Swing it back a little bit. Let's see if we can get the motion right. No, it needs higher pressure. I think we got. I think we'll have to reconvene back at the open mic and get this thing working. This is not a space-ready device by any means. I'll try going straight to the...
Well, Mark, this is an amazing attempt, man. It looks really cool. I can see what you're doing with it. It's really well built. I mean, it's just little bugs, you know?
It's little bugs in the system, pretty much. But it's... what we're hoping for now is for it not to work, because this is, by all means, just a null test. Control freak just wants to move.
It is interesting. It looks like it is moving, though, even without the gyros, without all that stuff.
Where's the discharge for that air pressure?
It's right by my hand. Can you swing it back? Swing the gyro arms back. Yeah, they should move toward the piston. Yeah. Nice. This system is kind of scary. I have scars on my hand to prove it.
Yeah, this looks like it could definitely bite you if you weren't paying attention.
Oh, it has. It definitely can bite you.
Can I see the scars, Dr.
Not right now. That's the idea of what we're going for with this. Now it's stuck in this spot over here. There's probably some mechanical bit that's getting it stuck. Anyways, it's got a lot to work on, and as predicted, this is a system that's very likely to self-destruct because of how difficult it is to build and just how much force is going into the darn thing. If the gyros were spun up, these can spin up to like 5 or 10,000 RPM. The forces involved would be astronomical. Like, it's likely that these aluminum 1/4-inch mounts over here might break, or the bolts would just shear off. That's why we have a double layer of padding to catch our hardware if it were to fail. And that's one of the reasons why I wanted to get this live, because very likely to fail with this system. But the idea is, if we have 3 gyroscopes at 120 degrees pulsing, we can overcome that translation issue. The translation issue, again, is with 2 gyroscopes going like this, swinging back and forth. What you have on a pendulum like that would just be up and down. It would just be going up and down. On the floor, it'll move forward. We've seen that with Mike Gamble's. But with 3 gyros, I think there's a way to overcome that. And each gyro's translation would go to the next, and they would all counteract. Nikola Tesla was very into the number 3. There are also 3 dimensions. If you look at this from this angle, it kind of looks like the corner of a CAD file. So I thought intuitively that 3 gyroscopes would provide some better results. Although it has a couple more tweaks to work out. For our next thing, I'll give an update on the Alzafon dynamic nuclear polarization experiment.
Yeah, and actually, Mark, if you want, I can walk you through. I have some slides that I could put up too, if you want to go over those real quick. You and I were going to do, in fact, I still want to do a podcast with you on that, but I can put those up too if you want.
Oh yeah, if you could put those up, we can run through those real quick before I show you the
Okay,
hardware.
yeah. Let me do that then. Let me do that. Give me 2 seconds. I'm just saving them to my hard drive now. Yeah, these are not ready. I mean, they're not finished slides, right? They're like almost there. But yeah, here, I will put these up. Give me 2 seconds, sir.
All right, I'm powering up the laser for a second just to show you guys what we've been playing with. Put this down for a second. Okay, we're using a surgical laser over here. This used to be used for cooking out cancer cells out of esophageal cancer, and right now I'm using it to cook or to excite triplet states in different samples for our dynamic nuclear polarization experiment. Just want to show you guys some of the latest things that we've added to the experiment. So I got it up and running. I'm going to leave it on low power over here. You can see the green going in there. Now, the sample is not in at the moment, but basically we have the fiber going to a little light breadboard or a circuit of light. It has a focuser. It has a 2 mirrors, and that brings it down into the chamber. And then there's a final mirror that pops it up into the sample coming in from the bottom. We've been using various AIs to gather all of the possible data on different experiments, and that have been run in this arena and figure out what settings we should have for our experiments in order to get the largest amount of bulk polarization. Are geared toward just looking at ways of increasing NMR's signal-to-noise ratio. So there are ways to increase NMR's signal-to-noise ratio without necessarily increasing, doing bulk polarization.
Okay, and I am ready.
Tim, do you have yours
are,
ready?
Sir. Yeah, I am. If it's okay, and
been ready.
you know what? Let me take everybody. Let me take everybody else out. It'll just be you and me. And so I will probably need to walk you through these
me,
slides.
by the way.
Yeah, you see, yeah. So it'll just be us. Let me and this will I'll just run through these real quick. So this won't take too long. Okay, I'll do share screen. There we go. Okay. So yeah, if it's okay, let me kind of run through these because again, these were kind of created for a podcast, but they're totally valuable here. So this is mass is the bottleneck. This is one thing you have been saying for decades. This took this out of one of your speeches. I went through all of your stuff, tried to get the key points. And so mass is the bottleneck, right?
Yeah, mass is pretty much in the two equations that stop us from traveling the stars. Either relativistic speeds, it's m equals mc squared, and then the rocket equation is all about this mass versus that mass and how fast they're moving.
Yeah. So let me go then to, and again, this comes from a very different slide deck, so I should apologize for that. The microwave clue, and this is the RB-47 incident. This was the inspiration for Alzafon to get started on the path that he did, right?
It wasn't really the inspiration. It was the light bulb moment where he realized the solution. The real inspiration was having a close encounter with a flying saucer, and then he realized, oh shit, these things are real. And being a physicist, trained at one of the most premier universities in the world, he wanted to get to the bottom of it. And this was the clue that got him down the path of nuclear polarization.
Okay. So then I went from there to the Alzafon so-called research lineage. I wanted to put this out there. I think that this is really important. You are working with David Alzafon. You are also working with a ton of NMR and dynamic nuclear polarization physicists. So the experts in this field, right? You are working with them. And again, you are collaborating with the family of the man who created this.
Yeah, not just David, also Daniel, the physicist's brother. Daniel actually had a hand in building this. This test setup was partially built by Daniel and George Hathaway. So yeah, we're working with the entire Alzafon family in that regard. Both David and Daniel.
Yeah.
On this experiment. We're also working with a new physicist from Cal Davis. who's very hands-on. I'm not sure if he wants his name mentioned yet, but this is a PhD physicist who works with dynamic nuclear polarization on an industrial commercial level. He helps big companies with their NMR EPR solutions for things like the sauce that goes into Domino's pizza. They had ways of detecting good and bad batches using NMR and EPR excited systems.
Okay, so then we're getting a little bit more hardcore here, what dynamic nuclear polarization does, right? And this was actually the reason that I got inspired to try and create this slide deck. So the work that you're doing, people either get it or they don't, and the vast majority of people don't because it is a niche area of science. Like one of the biggest things that you have told me is that people mix this up with NMR, and I actually have a slide on that coming down the pipe, but in terms of what dynamic nuclear polarization does this kind of reflect what is happening, I guess?
Yeah, dynamic nuclear polarization, as David Chester pointed out the other day, there's actually many different types of ways of achieving nuclear polarization, which is the ultimate goal. Nuclear polarization being the orientation of subatomic particles, or protons and neutrons. And if you orient the subatomic particles, the idea is that gravity would be oriented as well. So right now, gravity, for all intents and purposes, it points out in all directions equally as far as we can tell. But dynamic nuclear polarization states that if you can orient the spins of subatomic particles, then the gravity would be oriented as well, and then you'd have certain directions that you can move without the effects of gravity. Now, there's another book that I wanted to bring up. I call these the so-called Russian Area 51 paper. This is Gene Stiko's book, Engineering Infinity. And basically, they had some papers from a physicist that was working in the equivalent of Russian Area 51 or S4. He was back engineering alien spaceships. His family had no clue about it until like near his deathbed after the Soviet Union fell. He sent over all his documents to his daughter here in the US. And when they opened it and started reading it, none of it made any sense. They kept on talking about this thing called neutron magnetism as being the main propellant for UFO thrust. And neutron magnetism is basically, magnetism is spin orientation. So neutron magnetism would be nuclear orientation. And they had many different ways of achieving it, including some that are just recently being discovered if you pass a current through various materials, and if you microwave things like dynamic nuclear polarization, or just have a magnetic field. Another thing that he mentioned, which is kind of interesting, is they had an entire chapter devoted to this, not UFO propulsion, but when you have large masses spinning around, like Earth or solar system or a galaxy, there is a degree of nuclear polarization that happens that orients gravity as well for large celestial bodies. And what this does is it creates points of stronger gravity and weaker gravity. It kind of focuses gravity. And that creates anomalies that we've been seeing with our telescopes that brought about the fantasy of dark matter. Dark matter doesn't exist. It's actually just a misunderstood nuclear polarization. That's what he was trying to get across. And he had all the equations to describe how this fits in perfectly.
Yeah, so going to the Alzheimer hypothesis specifically, he's saying dynamic nuclear polarization can modify gravity. And that is exactly what you're saying. And Alzheimer actually did experiments that demonstrated this. You have done experiments that seem to support the same thing. So we're seeing hints of this, right? So this DNP effect, again, this DNP itself is established. It is used in industry. You mentioned Domino's using it to check sauces for contaminants. It's also used by pharmaceutical companies to check purity of batches. It is very well established. What you're saying is, hey, we can use this for something else, and that's the Alzheimer hypothesis, right?
Yeah, it's pretty much by orienting the spins of subatomic particles, we would also affect the way gravity interacts, and the way and gravity and inertia have they have a commonality. If you affect one, if you affect gravitational mass, you're also affecting inertial mass. So the hypothesis is that if you can make matter weightless along a plane and axis, you can shift the way mass interacts with the universe. You would essentially be able to do a 90-degree turn at 10,000 miles an hour along the free axis, the axis that is loosened from the restrictions of inertia. And that would also allow Drew's stuff, which we saw earlier, to actually do something, because if you have a craft that weighs nothing, a tiny bit of thrust goes a long way.
Oh yeah, that's a good point. So the reported weight signature, right? And this gets more into the testing that you've done. I have seen your testing up close. You are way beyond me in terms of the physics and technology, right? But I've kind of seen indications of this. There's repeated microwave cycles, and basically you're looking at those cycles to see if the resonance appears and if weight change happens from that, right?
Yeah, I mean, their test was probably running at a much lower frequency to allow for these types of measurements. This test setup, the way it's built and the proximity from the sample to the sensor won't allow us to measure mass changes or vibrations in the sample this closely.
Okay.
So you have to experiment. I can't physically replicate these kind of results and see as the microwave pulse happens whether the weight change happened right then or was it a couple microseconds later. We have to actually add filters to reduce the amount of data coming in from the sensor because there's just too much environmental noise. We want to see whether there was a weight change over a span of a second, not a microsecond.
Yeah. So then another area, and I'm just going by stuff that you have told me in the past, right? X band versus S band. The basically we're talking about the frequency, and lower frequencies may improve the experiment. This has been an area that you've mentioned a lot of people have confusion about when they get into it.
Yes. So with higher frequencies, the industry standard is to go for higher frequencies. And the reason for that, I believe, is because nuclear polarization can happen from just a magnetic field. So the stronger the magnetic field, the more nuclear polarization you're going to get off at the start. You get a running start when you have a 3 Tesla versus a 20 Tesla field. 20 Tesla field is going to knock it out of the park in terms of nuclear polarization without doing anything. Now, if you add all these other systems to it, microwave modulation at the lower frequency, you're able to pump that up even higher, many orders of magnitude. But if you start at a high point, you're able to, push it even higher. The problem is that only works for dielectrics because microwaves don't really absorb very well into conductive material. Now, conductive material like metals like aluminum or iron, they penetrate very to a very small degree, but nuclear polarization or electron paramagnetic resonance, which brings about dynamic nuclear polarization, works actually better in metals than it does in dielectrics. It's not used very often in that process, and there's no commercial equipment that would utilize metals, because they don't normally do those kind of experiments. They normally work with dielectrics like aspirin and pharmaceuticals. So the frequencies that you want would be completely different. So we started with the lowest commercial grade frequency, and that was in the X band, 9.5 gigahertz. And now we're moving down into the S band, which is 3 gigahertz. This line of thought was the same thing that Daniel Alzafon had, and the same line of thought that George Hathaway had, and it was also inspired by your first slide, by that microwave clue, because there was a pulse coming off of the UFO that was at 3 gigahertz. Oh, and yes, about Amy Eskridge. Yes, they were working on something similar. Amy suggested that we try orienting it towards between Earth's spin and nuclear polarization. And I actually was recently contacted on X by a guy named, I think it was Daniel, who actually suggested this to Richard's dad back in 2016. When he was working with him. And we're working on a replication of that over here. We put one of our electromagnets on a kind of pedestal thing aimed at the North Star. And we're building a test rig that would allow us to get the weight measurement inside the microwave chamber in there. So this is roughly aimed at the North Star right now. And that would give us, we'd call this the Eskridge Alciphon experiment, because it's a combination of the two of them.
Yeah, yeah. Well, and you are working with Richard, which is really exciting. It is so exciting to see you collaborating with Richard. So that's wonderful to see that relationship firming up. And then again, you were working with, you're working with David. So again, all of the experts in this tiny little field have good relationships and they're working together. So I want to go to this one now. Again, I'm going through my list of things that you've told me are like, I don't know what we call it, sticking points for people's understanding. So to bring it back to the DNP, laser assisted DNP and NV diamonds. So you are going to triplet state DNP, which is like a niche area in a niche area, right?
So this is a nitrogen vacancy diamond. It weighs 1.2 grams. It's, as far as I know, probably the largest nitrogen vacancy diamond ever made. It was made right here in New Jersey by US Diamond Technologies, made specifically for this experiment. And this is our sample that we're running right now. We're shooting light, green light through it. What this does, the whole idea of triplet state enhanced dynamic nuclear polarization, what it does is it gets electrons in one orbital that are pointed in the same direction. Now that is an unstable state. It's a high energy state. But if while they're in that high energy state, you hit them at their Larmor frequency, meaning you excite them with microwaves while they're in that high energy state, the coupling to the core goes up by orders of 100,000 to millions. Instead of going by orders of thousands, we're talking orders of millions times the NMR enhancement. This is not theoretical. This has been proven on a test bed, actual experimental, and there are many papers on this. This is a relatively new field. We're talking the last 5-10 years. Takeda, a team in Japan, was one of the first ones to discover this ability with pentacene crystals, and nitrogen vacancy diamonds were one of the latest things that are able to use this technology. One of the reasons why we like nitrogen vacancy diamonds is because the pentacene crystals, they only work for a couple pulses. You don't get much experiment out of them before they burn up. They're not very good with dealing with heat. Whereas the diamonds, they're diamonds. They can handle the heat. So yeah, we have the diamond made, and we're working with that as well. The main problem actually with the diamond has been the epoxy to hold it onto the stick. So we're trying to have a glass blower actually make a custom mount to hold the diamond so we can get rid of the epoxy.
Okay. So let me go to my last slide here, NMR versus dynamic nuclear polarization. Again, in terms of points of confusion, AI systems get confused, people get confused, textbooks get confused. So can you help elucidate us on this? Because this seems to be something that everybody has trouble with.
atoms of everything process along the magnetic field.
Oh, sorry,
And
Mark, I lost you
use,
for about,
it's
I lost
normally
you for about 30 seconds, I think. Sorry, could you, I lost you. Your signal cut out. I think you're too far from your repeater.
Oh, okay. So let me just repeat that. So we're talking about nuclear magnetic resonance versus electron. Can you hear me now?
Yeah, you cut out again, but now you're back. So okay, give it a try. For some reason, something's going on, but
yeah, I'm going to leave the laptop over here and stop moving around. So nuclear magnetic resonance is what we're most familiar with. It's the process that works behind a MRI machine. You have a magnetic field, and you're exciting the atom as a whole. Picture this as an atom. The entire atom is wobbling around. You excite it into a high energy state. Now it's upside down, wobbling around. You stop the excitation. It flips back over. And in the process, it pings out a megahertz signal. Now, this process, that we usually do it with hydrogen. And with this process, as it pings down, you're able to learn a lot about what that hydrogen is attached to, where it's located, how many hydrogen atoms there are. You're even able to tell what atoms the hydrogen is attached to. Like if it was attached to a cesium or a calcium atom or a carbon atom, any atom that it's attached to would have a sideband of frequencies. So you'd look at these scatter plots and you see the main frequency from the hydrogen over here, and you see all these little peaks of frequencies that are a couple hertz off, or like a kilohertz at most. It's all in a very small area. And then over time, you're able to see how those decay. So you just ping it once and you're able to see a whole bunch of data come back, and you're able to know what the molecule is. So it's a way of probing molecules. It's a great way to discover what they made in their latest batch, at Pfizer. One of the problems with that is it's not very sensitive. Now, in order to get it more sensitive, what you need to do is dynamic nuclear polarization. You need to get inside the atom and take the individual components of the atom and make them dance together. Now, if they're all dancing together, then suddenly the atom, instead of being able to absorb just a tiny amount of energy in its overall wobble, are now able to receive a lot more energy and then expel a lot more energy in their downsweep. Now, dynamic nuclear polarization or nuclear polarization, there's many ways to achieve it. And we also believe that is what creates this anti-gravity or inertial canceling effect. And NMR,
Awesome.
by the way, according to the theory, should not make any effect on the mass other than the magnetic field itself. Now, there was a study done by a professor out in Europe. What was his name? The guy who keeps trying to debunk everything.
Timar.
Yeah, Martin Timar. Now, Martin Timar used NMR in his experiment to try to run the Alzafon experiment. And what he noticed was there was no weight loss from the NMR, but there was weight loss when he put it in the magnetic field.
Okay.
Now, that fits exactly with the theory of dynamic nuclear polarization and Alzafon, because the only thing in that entire experiment that would create nuclear polarization is the magnetic field. The nuclear magnetic resonance will not do anything for this. Just the magnetic field does something. And that's exactly what he saw.
Amazing. So that's yet another indicator. Okay, well, Mark, that was it. That was my slide deck, man. I actually had more, but again, it was for a podcast interview. I am overwhelmed with joy that you were able to run through that for us, though. I'm going to break that one out too and put it up. I'll put it up on Twitter. I'll get it up on some of the social networks and stuff. And the reason is because so many people have been confused about DNP, and that's not their fault. It's a really complex niche area of science, man. I mean, you are pushing into an area that like nobody has been in before, right? So,
And I think there's a bit of a cover up there, because this is one of the only areas in science that has one book written on it. You would essentially, what we're doing is we're using electromagnetism to influence the strong force. The strong force is the gluons that hold the subatomic particles together in the core of the atom, and you're influencing how the spins of the subatomic particles. So you're influencing the strong force using the electromagnetic force. And that mechanism has only one book written on it, from 1963, Dynamic Nuclear Orientation by C.D. Jeffries. You could buy it on Amazon for, I think, $5,000 used, or you can get the PDF copy for free. But it's very interesting that an entire area of science, which seems to be fundamentally important, has only one book written on it, and you can't take a college course on it.
yeah, very, very niche, very niche. And again, you dominate this area, I mean, you were connected with all of the top people, the legacy of all of the top experiments. And so it's a wonderful to see a little community that's forming around your work. So yeah, congratulations, man. You're making it happen.
Thank you. Thank you very much. And we're not going to give up on the triad or the 3 gyroscope machine. I gave a little bit of blood for the cause today. You could see why we tried to have it live, because that thing is scary. That thing is scary powerful.
Yeah. That way people are here in case we need to call an ambulance for you.
Yes.
Well, let me bring everybody back in. That was just a lab update, but so we should put our hands together and clap for Mark. Mark, congratulations. Oh, and let me see. Jared is here and hiding, and I think Curtis abandoned us. Curtis is like, too much for me today, guys. So
Jared is actually working with me on the experiment as well. I've come to notice that Jared is our AI whisperer on the team, and I gave him all of the different specs and the different things that we can change in the experiment to try to whittle down what we should try, what specific ranges. The problem is we can't just run this experiment for an hour. The thermal effects on the diamond and the way it's set up, it just gets too hot too quickly. You have to run it in like 30-second spurts. So we're going to be trying to whittle down exactly what it is we should try. And I like Drew's advice of only change one thing at a time. It's kind of difficult to do that in this case, but we might have to find a way to do that and get an entire test process going.
Well, and James Woodward used to do that when I visited his lab. Now, the downside to that, there is a drawback. The problem with Jim's stuff was he had a very sophisticated setup, and it took him a while to build it. And so the change one thing and retest added a lot of time to his test cycle, right? But
yeah, I mean, in this case, it wouldn't add much time because the test one thing is turn a knob.
Yeah, and for him, it was like build a stack of piezos and wire it all up. And, there was a lot going on there. So, Jared, do you have something to share with us? I'm not even sure what Jared is. Jared's on the floor.
I'm doing electrical work. That's why I heard my name and I came running back. But I'm doing electrical work right now for one of my projects. And
okay. I
so
wasn't sure.
that I don't get in trouble with any of the agencies that say no, you must do things this way.
So
I'm not going to screen share that.
On my list, I'm hoping to do like an official formal podcast with Mark, the next week or two, because Mark's traveled a lot. And then I also want to do one with Jared on Jared's growing collection of UAP samples that he has analyzed. And that information is out there. I think the problem is we have overwhelmed the internet, right? Like there are so many bits and pieces floating around. It's like, yeah, we know Jared's doing stuff, but we're not exactly sure what.
Yeah, so I'll give a super short, like 30-second, 60-second here. So I went through all of the different samples and I spent a good chunk of time on arts parts. After I spent enough time on arts parts, and when I say spent time, I mean I'm building software programs to analyze some of the different resonance modes that this thing could potentially undergo. What I came away from that with was a hypothesis, an educated hypothesis, that it's doing some kind of plasma boundary layer control mechanism. That said, the bismuth lead layers, when you look at the error report, the ratios of those are right smack dab in the area where it looks human made. It's bismuth lead solder within like a % ratio. So I'm looking at this like, okay, so this might be something that humans could build, and it's doing a plasma boundary control layer. So then I took that and I went through all of the different UFO report sightings and came away from looking at this from the lens of, yeah, it's doing some kind of plasma boundary control around these craft, and that explains 2/3 or more of the observables. So then from that, I started going down the rabbit hole of trying to identify every last shred of information I can find on the program, right? So thanks to AI being so dang impressive nowadays when you learn how to use it properly, meaning have it be able to go collect the data, analyze the data, predict the next data that you need to collect. And you just iterate that loop over and over and over. And you can build this massive web, this massive picture on what it looks like, who was doing what, and where they were doing it. And the most important thing, when they were doing it. So last point that I'll say is the most important window of time that I'm focusing on is basically everything leading up to the early 1970s. It seems like after the early to mid 1970s, that's when you start getting a lot more noise in the signals. There's a lot more people spouting ideas left and right. And the aliens told me that I need to meditate the plasma into a heart shape or some shit. I don't know. So I'm keeping it to the most like rigorous thing that I can to be able to try to tease out just little bits and pieces of, if I wanted to build my own thing using only publicly accessible information, nothing classified, only publicly accessible information, is there a way to be able to fit enough those pieces together where you can identify this is the way that the program, specifically the individuals identified as being program members, who then publicly spoke in little bits and pieces here and there. And when you fit all those pieces together, it comes out with this narrative of, yes, you do this thing. This is the thing you do. So that's where I'm at right now. And in the meantime, I have other experimental stuff that I'm setting up that I'm not at liberty to show at this time.
Okay, well, there we go. And oops, hit the wrong button. Yeah.
Somebody in the group is asking
wrong
about the
button again.
Graviflyer. Are we going to go back to Graviflyer? Are we done with that?
Okay, there we go. Sorry about that.
Graviflyers up there. I'm
Oh, wait.
trying to get them to collect dust. They're not collecting dust fast enough.
I have been getting questions about the Graviflyer also. There's the Graviflyer has reared its ugly head once again. I had someone email me earlier this morning about it. They were like, "Where's Alexi at?" I'm like, with Waldo.
I still want to try my version of Graviflyer. Replace Tesla coil with an RF antenna thing.
The last we heard about Alexei was that he was saying that he had to go back to Russia to go take care of an aging parent. And he was pretty certain that he was going to be called back into military service as a minesweeper. And so from what he was telling us, if what he was telling us was truthful, he was basically saying like goodbye for good, like I'm going to go die. So, and that was like 2 years ago. So a year and a half or 2 years
Going
ago.
back to that. Okay.
Yeah. So he was living over in Western Europe. And then the last we heard from him, he was leaving that to go back home to Russia to go take care of an aging parent that was like, deathbed aging kind of thing. And then that was the last we'd ever heard from him. So I think I'll say it again. I think the Graviflyer is an excellent project for people to get their toes wet on just trying to build an experiment. That said, I would not say that anybody should go into it thinking that they're going to see actual thrust. I know that Nathan Bunton over at Old Man Builds seemed like he may have gotten some thrusts. I have only very briefly corresponded with him since he got those to try to like follow up and verify that. But again, like the Graviflyer is like it's a stew, it's a pot where you just throw all of these different things in there. And because there's so many variables, you're never going to be able to quite figure out, well, was it this thing or that thing or that thing? But in the process of trying to learn how each of those variables affects things, you're going to become a master engineer really fast if you put in the time and effort and energy to not just build, not just record your tests, but then to go follow up and identify this is how RF affects a sheet of metal that then affects electrostatics on that metal, right? That kind of procedural thinking makes for a really good engineering course.
I see folks in chat saying that Alexei was a charlatan. I don't know what to think. I guess my thought would be, I've seen a group of 10 to 14 people work pretty diligently. Some of them, I mean, Jared, you put in like day and night for like 2 or 3 years on that thing. And all of them failed to replicate his stuff, and they failed to do it using equipment that he mailed them, right? People were buying stuff and he was sending it from, I mean, this was handmade by Alexei. He's like, here, build this, fly it, it will work. And it never worked. And so for me, it's like I want to believe, but I'm increasingly skeptical.
I know.
What about Hutchison? Hutchison was the same thing, but we know Hutchison actually worked.
I think the big difference with Hutchison was it was TV crews that caught it. Like, it was TV crews that came in. So I can tell you the thing that killed Hutchison's reputation, and this is the dumbest thing ever. This was like 2005, I think. He had a TV crew come in, and he sent me a video of it that he shot himself. And he's like, look, I made a lifter. And it was like a single wire running to a Tesla coil, going to a little toy UFO, and it was bobbing up and down. And I was like, well, John, I was like, that's cool. That's not really a lifter. And he's like, yeah, the TV crew wanted something that would move around, and we ran our regular equipment, and nothing happened that day. He's like, so I knew that this would move from electrostatic force. I'm like, okay, I get it. So the internet, because it's the internet picked that up, and they said, see, it's a fraud. Everything he does is fake. And I'm like, no. That was like 15 years after his original experiments, completely different setup. He never intended it to be anything different, but the TV crew pushed him to do it. So, you know,
I like Todd's comment. And Hutchison, according to Hathaway, Hutchison was probably psychic or had some mental effect on it, because as soon as they put him on meds, he couldn't do the effect anymore.
Yeah, I mean, George was, well, and you guys were there. George was pretty clear about that. I mean,
he was pretty certain that it had something to do with the man himself. It wasn't just settings on the machine. It was, he was connected to something or influencing the outcome of the experiment in some way that he couldn't understand, other than like telekinetic abilities. Now, it's possible that Alexei is doing the same thing. I know Jared was on a couple of calls with him where the equipment, the thing, as soon as it started doing the thing, the laptop would burn up, and then he'd have to go and fix the laptop. And Jared, you did get to a certain point where you heard like the whirring change and the RPMs change. You did get a couple of things to happen, right?
Yeah, I reproduced. So there was like, I don't know, 10 or 15 different effects besides lift that were like the mile markers you're supposed to look for. And I got like all of those, every single one. I got erroneous electronic, interference type stuff, like EMP type stuff at a distance, right? I'm turning on and off the touch bulb 30 feet away through multiple walls, freaking out the wife. I managed to get the sound changes in there. I was able to identify some of the interactions between the charged spinning rotors and the RF, and how that RF would cause a speed change in those rotors when it was pulsed in different ways. The one thing that I got while Tim was there, this was a great thing that Tim was there and was able to like record it, was how the ultrasound, the little piezo buzzer on top, you could turn that thing on, and at milliwatts, that thing is able to affect the charges on the spinning discs enough to cause their RPMs to change, and you could hear the change with the beat frequency. So there's
milliwatts of buzz is changing the RPM of something that it's like barely even connected to.
Yep. So there's a lot of interactions going on there. However, one of the main things that a lot of people, I think even including Alexi, tried to like reiterate was like TT Brown. It's kind of like TT Brown effect, right? You got the positive on the top and the negative on the lower. And it's, when you actually go through Brown's notes at 30 kV, which is what we were running, what Alexi was running at 30 kV, Brown didn't get like barely even a gram of thrust in any of his iterations, years and years of iterations. He didn't get more than a gram at 30 kV. It wasn't until he got up to like 150 kV, you were starting to get like 20, 30 grams, right? And the Graviflyer weighs like 1,200 to 1,500 grams. So, and I did manage to see a few instances where it looked like I got some vertical thrust in like very tiny amounts. The best one I saw was some translational thrust when I got everything lined up speed-wise and the rotors were perfectly matched within an RPM. I was able to get it to pulse in a sideways motion, which again, I think it's all gyroscopic at that point. As far as actual lift of the Graviflyer, my present conviction at like 90+% certainty, strings, dude. Lifting the thing with strings.
Yeah.
There's a lot of great stuff with the Graviflyer for electronics interactions. Lift is not one of them.
Yeah, so that would put it in the hoax category.
Where I sit.
Yep.
I could be wrong. I could be totally wrong.
Well, you heard it from a guy who spent years staring at it and building them and testing them. So, but again, it could be just like Mr. Hutchinson. It could be that you need to have this psychic telekinetic ability.
And Alexi did use psychic stuff on it. So he told us how he would rub his hands together to build up his chi, and then he would use his hands to feel the magnetic fields there. If you dive down the chi rabbit hole, that is kind of a thing. Like they talk about like the magnetic fluid of the chi energy or some stuff. And so, yeah, or maybe it's just electrostatics on the hairs on your skin or something. Either way, feeling the size of that electromagnetic bubble, I prefer to just use my tri-field and other equipment to identify the boundary and the strengths and gradients of those fields. But Alexi used chi.
You could totally feel static fields. I don't know about
but you can't feel chi.
you can feel magnetic fields too. I've felt when I had rotating magnets, I put my hand near it, I was able to feel the vibration from them. Strong magnetic fields that are changing back and forth, you can feel it a little bit.
And that's another credit to Alexi. He talked about how it was kind of like a vortex of this field around the thing. And I measured that with the tri-field. You could see that you're getting like 100 hertz or whatever of the magnetic field at the equator. And then as I would get up to the top, I'd get it, or maybe it was like 30 hertz. And then I get up to the top and it was like 150 hertz right at the very top center. So like this whole swirling thing is getting tighter and tighter at the top. But again, it's the Graviflyer, dude.
Yeah, I mean, needless to say, we're not working on it actively anymore. But if anyone wants to get involved,
there's still a Reddit chat. You can go search for Graviflyer on Reddit, and that has all of the resources you need to go build your own and see, the general information we've given out. We got the links in there for the interviews that we did with Alexi, where he was doing live lifting tests of this thing in his house. If somebody wants to go down the rabbit hole, that's where I'd say to go. But
yeah.
I mean, maybe we'd have another Hutchinson, like, who is just intuitive and very autistic, who can.
So let's, guys, if it's cool, let's open things up for open. I mean, we're in open discussion, so let's just make officially open discussion, and then.
I would say if anybody wanted to get into the alt engineering field, the absolute best place to start is with what Drew showed off today. Drew showed off, look, here's somebody that took our freebie, publicly available, accessible information on how to build a stupid, simple thruster. And this is what they did to get it all going. Like, the barrier to entry into alt engineering has gotten a lot lower thanks to Drew making it so easily accessible. Now, granted, the thrusts that you're getting are so much smaller that you got to be more careful about measuring those thrusts. But Drew and Charles seem to have found the sauce that we've all been seeking, at least one version of it.
Yeah, I mean, everything that I understand about it is the genius behind what they've done is careful experimentation and observation, right? Like the stuff that he's seen has been there the whole time. They were the only people who were able to slow down, dig in, and really say, let's isolate this and build off it.
Yeah, they are not the discoverers of this effect. They're the ones who took it far enough to actually do something with it.
Yeah, yeah.
And it's like that in there's a lot of scientific discoveries that were discovered but never turned into anything until somebody came along who commercialized it.
It would make sense that this has kind of languished in obscurity for so long because it is so mixed in with ion wind, right? I mean, it's really hard to kind of pull those two apart. So it makes complete sense.
Yep.
So also I think it goes totally against the narrative of the mainstream physical landscape, right? That such an effect can even happen, right? So even today, mainstream physicists will scratch his head and ask, where is the momentum going to, right? Where's the energy coming from if you do actually work with it for some time? And there is no good theoretical explanation still to this question. And I think this is so important because from experiment showing there is an effect to now they don't even have a complete description theoretical of what it is. But I think especially with some of the slides, you saw that the understanding is at a point where it becomes very interesting for the engineering standpoint. They know what to optimize for. So basically put more area that is very workable into a smaller device and try to get rid of all the mass you don't need that gives you actually propulsion, and then try to scale it up. And that's going to be great to see how fast they can succeed in scaling up this thruster pack that they're trying to build.
One area, if I can share screen here, there is a patent that I would recommend folks go take a look at. Here we go. So when you go back down into the history of TT Brown, which is kind of what Drew's team is doing, is a newer version of TT Brown stuff, right? Much better thought out. But there's this one guy named James F. King. Well, him and Bahnsen from the Bahnsen-Brown lab, right? Him and Bahnsen had one patent together about textiles or something. Anyways, that textiles patent just shows that they had some kind of working relationship. Well, this patent came out 1964. The Bahnsen-Brown lab ended like 1958, 59. So within just a few years of the results they got at the Bahnsen-Brown lab, you got this guy coming out with basically an ARV looking craft 24, 25 years before the Norton Air Show ARV from 1988. And this guy thought that it was all about magnetohydrodynamics, which you got to be careful with MHD stuff because there's a lot of bad info out there on MHD where people try to make it seem like actual magic. I don't know about any of that, but what I do know is that if you ionize air and then you magnetically yank that air, you can get thrusts. You can get a lot of thrusts. It's just very energy hungry. So yeah, I'd say for people wanting to go down the rabbit hole and see how this tech could maybe potentially evolve beyond Drew's tech, look into Bahnsen, Agnew Bahnsen's patents from the early 60s, and look into James F. King.
And just for to put this in layman's terms, this is the equivalent of taking a rail gun and flipping it inside out. So instead of moving a projectile forward with a magnetic field or a static field, you have all that on the outside, and you use that to propel your craft forward. Now, this is real technology. There was actually a company, I think in Japan, that made a boat using MHD technology. It had nothing in contact with the water but magnets just turning on and sweeping the water back and forth, and that would move the boat. Very energy hungry, wasn't very efficient because mu and epsilon are the permittivity and permeability of space-time, they're not zero, but they're very low. They're very close to zero. So you need to overcome the inefficiencies to actually couple to it. But if you can somehow increase that number before coupling to it, then you have a bigger hook to catch onto. But this is the stuff that Hal Puthoff talks about a lot too, changing the permittivity and permeability of space-time, which, by the way, is totally doable. I think we do it all the time. We just aren't measuring. We're not constantly measuring the permittivity and permeability of space-time. We tend to do that in a very controlled environment where it's not being perturbed. But if you were to go up to a transmission line or an RF transmitter that's putting out like a megawatt of RF energy, I promise you the permittivity and permeability of space-time right next to that antenna in the near field, it ain't regular mu and epsilon. It changed a bit.
Yeah, that wouldn't surprise me at all. I mean, there are a lot of these things that we're still learning and still discovering, you know? And so, but like this stuff is moving forward really fast right now. And I think that AI is accelerating that in terms of letting people go through these vast amounts of papers and research and just find things more quickly and correlate things more quickly.
Amen to that. So, Tim, when is our next open mic?
So about 2 weeks here. I'll check the calendar. So one of the things that we've been talking about is winding down these webinars, just keeping doing the open mics, but taking a break from the webinars. And part of that is we outrun what this community is able to produce, you know? And so, you know, rather than like, you know, just begging for presentations every few weeks, you know, it's easier to just take a break for a while. Part of it's that. The other part is we are all super, super busy. Okay, so open mic is on the 12th. And then, yeah, and the next one after that is on the 10th of October. So September 12th and October 10th.
Sweet. Mass Inertia, I have your video up on another channel, and I would love to talk to you. Playing with inertial propulsion is a lot of fun. It's mostly engineering, mostly braking stuff. And yeah, anybody who's in that field who wants to talk would love to talk. I do have the Mercury Vortex engine in mind. That is our primary goal, is to get whatever we learn from these gyroscopes into a more solid state version of it, where we don't have a bunch of moving parts in a moving part system, and it's more solid state, you know, glass blown and whatever, so that you can actually get this effect without all the vibrations and all the destructive shit. But yeah, I will be reaching out to you shortly.
You know, I have a real thought. People get pissed at me for saying this, but okay, so with inertial propulsion, the complaint is that it's slipstick or that it's constrained in one, right? And like, so one example video is the Roy Thornson's canoe. And they were like, well, but it's constrained. So if it's pushing down against the water or up against gravity, you know, on the upstroke, right? If it's constrained in 2 dimensions, then of course it can produce forward thrust. And I'm like, okay, yes. So even if it's limited for a space drive, right? Even if it doesn't work there, we've pretty much proven without a doubt that this thing works for like boats, cars, land vehicles, maybe aircraft. I mean, like for conventional applications, inertial propulsion is pretty much proven to work.
There was this guy, Harry Styles or stuff like that used to present, and I don't know, and he probably bought a ride on that's what he said. I don't know what happened to him.
Yeah, he had Sid and the centrifugal inertial
Yeah, he's
device.
still around.
Yeah, he's probably watching right now. His device used magnets that would like offset a little bit at one point.
Yeah, and then my thought is like, again, the mainstream is they throw the baby out with the bathwater here, right? Like, okay, I mean, from what I've seen with inertial propulsion, I'm like, yeah, send it up in space and test it. I would love to see the results. But even if it absolutely fails, like Roy Thornton proved, you put this thing in a canoe, right? And the reason he used a canoe was because it didn't have resistance either direction. So you know, like like with a normal boat, it's going to prefer to go one direction because that bow is shorter than the stern, or it's narrower than the stern. He used a canoe because it was the same in both directions, and it produced noticeable forward thrust. So
Yeah, that was pretty slam dunk. The canoe moving through the pool, that seemed pretty conclusive that the thing was actually working. I
Yeah.
just want to respond to Bernie for a moment. He says that I'm supposed to be getting money from Mossad, and he has evidence. So, Bernie, if you have any evidence that I'm supposed to be getting money from Mossad, please send it my way. I haven't got those checks yet, and we can use some extra funding. Sure. I didn't know Mossad was giving out money for this kind of stuff, but yeah, it's cool.
I think he wrote Moss ad.
He
Maybe
meant
that's
is it like an advertisement? No, I think he
No,
means
no, you're
Mossad.
getting money from the Moss people.
Yes, but if he has like bank statements or like, because they probably sent it to the wrong account, and I need to go back to whoever's sending the money, make sure we get it, and we could put it to good use. Bertie, I'll tell you what, I'll even give you a 50% kickback. 50% kickback on any money that we receive from Mossad, okay?
Okay. It's like, Tim, don't cry. Don't cry. Okay. No, sorry. It's fine.
Bertie has the best weed.
Yeah, I don't know. Well, and then so I mean, I don't know if it's worth announcing or not, but I've taken a role with M31 Capital, and I'm really excited about that. I'm in a transition period. I'm coming on board. You know, and
Very
so,
excited for you, Tim. Yes.
well, thank you. Thank you. And the thing that surprised me most, they are into all of these areas. They are most excited about consciousness. So it's like I have to brush up on my consciousness stuff. So,
And Tim, do you want to say what you're doing for him?
tech scouting, and I'm really excited. And that plays off of the networking and the podcasting and all of the stuff that I've been doing. So yeah, it's networking and trying to identify ideas and companies that have value. Yeah, if you guys want, I'm happy to. I'll put the website up. Oops. Because there are 2 or 3 different ones.
Actually, no, it wasn't Amy's email list. It was from Estes Park and Jack Sarfati.
Oh,
that was
okay.
the first APEC was a combination of those 2 email lists, and I just sent out an invite. Starting
Moss
in half an
ad
hour.
Mark admitted to starting from taking Amy Eskridge's mailing list. RIP. Okay, so yeah, I don't know. I mean, here's something that I would love if Bernie can put in. So Aiden Schaefer passed in police custody. That's the last anyone I've heard of knows of that. I do know that he was arrested that second time. So in January he was arrested for breaking and entering into his ex-girlfriend's house in wherever he was, in New Mexico. He was arrested a month later for arson on the same house. I have not heard what happened after he was arrested, and I have not met anyone who knows. I haven't even heard rumors. Just he died in custody, which I don't know. I don't know.
So yeah, Bernie, if you have any info on that you want to make public, so like people can get some closure on Aiden and like kind of close that loop, because all we heard is he went to jail and died. Like that's not good enough for all of us who knew and liked him.
I don't know. I mean, the other thing that I'd heard, and like I'm going to sound like a PSA announcement now, but like I have heard that he was doing a lot more drugs and alcohol in the month before he passed. And I've heard that he made statements to the effect of, if I do enough of this, whatever he was taking, it'll let ET talk to me. And so a big part of that is, my takeaway is focus on mental health It's not a joke, right? Like I go on Twitter and it's this conspiracy and that conspiracy and the other conspiracy, but like the mental health part of this is real. It's not like a game online that people play. Take care of yourself. If you feel like you're getting into not just this area, any area, all of this fringe type stuff, if you feel like you're getting in too deep, take a break and walk away. It doesn't have to be forever. Just take some time, you know? And then the other thing, again, I feel like an old person saying this, but like have some normal activities in your life, right? Like I exercise every day. I have an elderly dog that I walk. That is super healthy because it gets you away from the computer, gets you away from the memes, and it gets you away from the conspiratorial world online. So, sorry, I know I fall into dad mode. It's my dad mode lectures.
Yeah, I see this mental state coming to many members of this field. And it kind of gets to your head because when you think about it, the stuff we're talking about here can change the world. And if you let that get to your head and stop focusing on the nitty gritty and what size screw you need for your experiment or whether your theory is sound, and you start looking at big picture and, oh, this is conspiracy and all that, you can go down some rabbit holes and end up in some really negative areas. And I've seen that with people before. I've seen that with Aiden. I've seen that with Amy. I've seen that with Jeremy sometimes. Jeremy, he found an amazing girl and he managed to get out of that. I've seen that with Jared. And I slap him over the face when he does it. But yes, it happens to all of us because it's kind of like we're working on some really cool stuff that has the potential to change the world. And like, you can let it get to your head. It can start to really drive you nuts.
Well, you have
loosen the tinfoil every once in a while.
Yeah, you have intelligent, sensitive people, right? And so you're intelligent and you're more responsive to ideas to begin with. And then we are outside of mainstream culture, right? We're outside of that consensus reality. You know, like here's what normal is. And we're saying, okay, I'm willing to experiment with things that are outside of that, right? So it's already kind of towards the edge. And then, you know, people get too isolated. They get too tired. I mean, you know, they have substances involved, God knows what. And it can push them over the edge. And that's, again, for me, having normal stuff in your life, normal relationships, right? Like normal schedule, trying to, you know, there's a reason that the rest of the world does that.
Todd, as far as Lexapro goes, Lexapro and all these SSRIs, Tim could talk to this a bit more. What they are is basically fake psychedelics. Psychedelics used to be our way of talking to our subconscious and fixing and working on the problems that we're having, why we're depressed and whatnot. And there were shamans that would lead us through these ceremonies. And then when they made it illegal because of the Vietnam War, companies found a way to tickle some of the sensors that those that psychedelics tickle and release just a little bit. So that's kind of like fake psychedelics. Yeah, new shrooms. Real shrooms work much better, and that's not any advice from me. It's legal in Colorado.
Yeah, my thought is like I'm big on exercise, fresh air, exercise, right? Just, I mean, that's what we've all for, and it helps, right? It's not a magic bullet, but it helps.
Go outside and look at the color green and touch the color green.
Yeah. And then part of that's associated is like getting out of your head, right? Because we all tend to live in our heads. And it's like, you gotta take a break from that periodically.
I would recommend dopamine addiction. That's what I have. I mean, running. That works very well.
Yeah. Well, running is good for people who can pull it off.
No, it's in your head because you don't get that thing if you do
need
other
to get
sports.
to that point.
Yeah. Oh, you do. Yeah. Slowly, but you do.
You know what I'm talking about, right?
It took me a few years, but yes, I did. Yeah. And I was in love with crullers and Boston creams. So.
Yeah. Well, I think some of that is like a change in life too, right? Like I just turned 50 and it's like I can't get away with a lot of the body abuse that I used to have, you know? Like I have to eat healthier. I don't have a choice. So I don't know.
Yeah, losing weight can help too. It kind of like is a snowball effect. When you're overweight, it's harder to work out, and when it's harder to work out, you gain more and more weight. So losing weight reverses that entire effect, and you can start working out more and burning more calories and getting back into shape. So
Yeah. Well, I mean, in a weird way, all of this stuff is off topic, but then I think in a weird way, it's also relevant because, I mean, like Amy was a tragic loss and Aiden was a tragic loss. And there have been other people, right? Mark McCandlish. Yeah. I mean, you know, and then there have been several others that have passed recently. And people are like, why does this happen? And it's like, my thought is a big part of it is because they get in too deep and they don't have the tools to reconnect and they just get lost, you know?
yeah.
Well, I don't know. So it's 3:30 p.m., guys, Pacific time. Do you want to go more or should we wrap things up for today?
I'm good to go.
Wrap things up.
Well, guys, this has been APEC for August 29th, 2026. I thank you so much to everybody. I'm pleased as punch to be able to get all of this stuff. Again, we're going to try and do a few more of these. I think what we may end up doing is ending APEC after our anniversary, like the 6-year anniversary, and we'll keep doing the open mic, and then maybe I have to figure things out, but I think maybe go to a quarterly or maybe a yearly, and that way we can really focus on the projects that are moving forward the most. And we won't feel pressured to, you know, hey, it's like in the middle of the month, who's going to speak? Do we have something? Because
don't push it if there's nothing there. Like,
yeah,
let it go with the flow a bit more instead of, oh, we need to do another session. And another thing I was telling Tim, and I want to hear from everyone, both in this call and on YouTube. I think running these conferences more in the winter is probably more important than the summer, because in the summer, you're doing one mid-July, mid-August, you're not going to get a full crowd. People are on vacation. They got kids at home. But if you're doing it in the dead of winter, when everyone's inside and on their screen, you're going to get a lot more attention. So it might be better to just skip summers altogether.
That's why making that decision, what Tim just said, you know, skipping and stuff like that in the summer is not a good place. Okay, because you feel okay, nobody cares. Okay, everybody's away. But in the winter, you don't feel you have that feeling.
Yeah, and actually, I mean, I already did my closing remark or whatever, but like, yeah. So one of the big thoughts is, this is just my thought, but this community is growing up, and so part of it is like, how can we help this conference reflect that? And one thing Joel has talked about, Joel has a working group for Heim theory. So for anybody who has Joel's info, or Joel, if you want to plug your info into chat, you know, or whatever, you know, like Drew has a working group. I'm not sure if he wants to just admit folks into it, but he has one for his work. I know Mark has one for Falcon Space, right? So part of it is creating working groups and then getting that out there and saying, hey, if you're interested specifically in DNP, here is a resource that you can use, right? And the same would apply to the Woodward effect. Theirs is not public, but like Curtis and Michelle and a bunch of other folks, they correspond and collaborate all the time, you know? So that's the way our community is. And I think it's good to open that up. And instead of just saying, hey, it's just one big community, say, yes, but there are also specializations, right? And some people are like heads and tails over like centrifugal propulsion. They're like, that's my thing. Whereas other people are going to be like, no, B-Field Brown, that's where I got to be. It's just what appeals to different folks.
So, but I think you cannot understate how important the APEC conference has been for the last 6 years as a center where a lot of people could meet for the first time, come together in the open mic forums and so on. So I think definitely the conference has a place in the future, and it's very important to have such a open and a big format, maybe not as regular. And as you said, so there are different groups, but also we started now to have some theoretical, like cross-talking meetings to get some different people and different ideas interconnected more, and stuff like this should also grow. But this is like, people have just to do it, right? So people from the community. It cannot be just on you guys to organize this kind of stuff.
Yeah. Okay. Well, guys, let me bail out on everyone for now. I guess we're going to shut things down. It has been absolutely wonderful, and again, I will cut these up and put up breakouts for these as well. I'm really pleased. Thank you again. And Mark, you had something?
Oh yeah, I just wanted to say let's give a round of applause for Tim Ventura.
Oh, well, thank you, sir. I hope I'm doing okay. I've been busy as heck for the last like month at this point, so I barely see straight, but I'm just trying to keep it together. Okay. Have a good one, guys.
Live long and prosper.